Close your eyes right now. No, seriously. Just for 3 seconds. What did you feel? A wave of calm? A sudden awareness of your heartbeat? That simple act you just performed is the same ritual your ancestors did 4 billion years ago. And what happens in those few seconds of darkness holds the secret to why you're still alive today. Hey everyone, welcome back to the channel. If you're new here, I'm so glad you found us. We explore the mysteries of the cosmos, the human mind, and everything that helps us understand this incredible universe we're part of. And today, we're diving into something that might sound simple, but is actually one of the most profound phenomena in all of nature. What happens when you close your eyes? If this topic resonates with you, go ahead and hit that like button. And if you want more content that helps you understand your mind and sleep better, subscribe and turn on notifications. Trust me, by the end of this journey, you'll never think about closing your eyes the same way again. Now, let me take you back, way back. 3.8 billion years ago, Earth was a violent, chaotic place. Volcanic eruptions, asteroid impacts, toxic atmosphere. And yet, in the primordial oceans, something miraculous happened. The first single-celled organisms appeared. These tiny creatures had no eyes, no brain, no consciousness as we know it. But they had something remarkable, a biological clock. They could sense light and darkness. And when darkness came, they entered a state we now call torpor, a primitive form of rest. Why? Because even these ancient organisms understood something fundamental. Constant activity is unsustainable. The universe itself operates in cycles, day and night, seasons, the expansion and contraction of stars. And life, from its very beginning, learned to mirror these cosmic rhythms. This wasn't just adaptation. This was survival, encoded into the DNA of every living thing that came after. Fast forward to 500 million years ago. Animals now had eyes, brains, complex nervous systems. But here's what's fascinating. Sleep didn't disappear. It evolved. It became more sophisticated, more essential. Fruit flies sleep. Fish sleep. Even jellyfish, which have no brain at all, enter rest states that look remarkably like sleep. Scientists at Caltech discovered in 2017 that when you deprive jellyfish of these rest periods, they become sluggish and less responsive, just like you after pulling an all-nighter. Think about what this means. Sleep survived 500 million years of evolution. Predators still needed to sleep, even though it made them vulnerable. Prey still needed to sleep, even though it put them at risk. Natural selection, the most ruthless force in nature, kept sleep because the cost of staying awake was worse than the risk of being eaten while asleep. Let that sink in for a moment. Now humans. We evolved about 300,000 years ago in East Africa. And our ancestors quickly learned that closing their eyes and entering sleep wasn't just rest. It was medicine. Ancient cultures across the world recognized this long before we had microscopes or brain scanners. In ancient Egypt, around 3000 BCE, the god of sleep was Shai, a deity so important that he was present at every person's birth and death. The Egyptians built sleep temples called Asclepians, where sick people would come to sleep, believing that dreams would bring healing messages from the gods. And you know what? They weren't entirely wrong. We now know that sleep dramatically boosts immune function. A 2019 study published in the Journal of Experimental Medicine showed that sleep enhances the ability of T cells, your body's disease fighters, to attach to and destroy infected cells. The Egyptians didn't know about T cells, but they knew sleep healed. The ancient Greeks took this even further. Hippocrates, the father of modern medicine, wrote in 400 BCE that sleep and wakefulness, both in excess, constitute disease. He observed that patients who slept well recovered faster. Aristotle pondered why we sleep at all, proposing that vapors from digestion would rise to the brain and induce sleep. Wrong on the mechanism, but right that something biological was happening. But here's where it gets truly fascinating. In ancient India, around 500 BCE, Buddhist monks were practicing something revolutionary. They called it Yoga Nidra, yogic sleep. This wasn't just about closing your eyes and drifting off. It was a conscious practice of entering deep relaxation while maintaining awareness. Modern neuroscience has now validated what these monks knew 2,500 years ago. When you practice Yoga Nidra, your brain enters theta wave states, the same brainwave patterns seen in deep meditation and the lightest stages of sleep. A 2013 study from the Swami Vivekananda Yoga Research Foundation found that 30 minutes of Yoga Nidra was as restorative as 2 hours of conventional sleep. Think about this. Ancient humans, without any scientific equipment, discovered that closing their eyes and entering altered states of consciousness was therapeutic. They didn't know about neurons or neurotransmitters, but they understood the result: peace, healing, clarity. Then we jump to the 1950s, the modern age. We had split the atom, invented computers, sent objects into space. But we still didn't understand sleep. Enter William Dement, a young medical student at the University of Chicago. In 1952, Dement joined the laboratory of Nathaniel Kleitman, who was conducting what seemed like a simple experiment, watching people sleep. One night, Dement and his colleague, Eugene Osarinsky, noticed something extraordinary. The sleeping subject's eyes were moving rapidly beneath their closed eyelids. They called it rapid eye movement, or REM sleep. When they woke people during these episodes, almost everyone reported vivid, bizarre dreams. This was revolutionary. It proved that sleep wasn't a uniform state of unconsciousness. The brain was active, sometimes more active than when awake. But Dement wanted to know more. What happens if you prevent someone from closing their eyes and sleeping? In 1964, he conducted one of the most famous experiments in sleep science. A 17-year-old high school student named Randy Gardner stayed awake for 264 hours, 11 days straight. Dement monitored him the entire time. The results were terrifying. After just 3 days, Gardner became moody and uncoordinated. By day 4, he was hallucinating, seeing fog and thinking a street sign was a person. By day 11, his cognitive abilities had deteriorated so severely he couldn't perform simple tasks. His immune system was suppressed. His body was falling apart. The moment Gardner was allowed to close his eyes and sleep, something miraculous happened. His brain immediately dove into deep sleep, the deepest stages, and stayed there for hours. His body knew exactly what it needed. Within days of recovery sleep, his symptoms vanished. His mind came back. This experiment, though ethically questionable by today's standards, proved something crucial. Closing your eyes and sleeping isn't optional. It's not luxury. It's not weakness. It's biological necessity. William Dement went on to establish the world's first sleep research center at Stanford University in 1970. He became known as the father of sleep medicine. And his research opened the floodgates. Suddenly, scientists around the world wanted to know, what exactly is happening in those hours when we close our eyes? This brings us to 2012, University of Rochester Medical Center. Dr. Macon Nedergaard and her team made a discovery that would fundamentally change how we understand sleep. They discovered that when you close your eyes and fall asleep, your brain does something absolutely extraordinary. It shrinks. Not permanently, but by about 60% in terms of the space between cells. And in that space, cerebrospinal fluid rushes in like a cleaning crew in an empty building, washing away toxic waste that accumulated during your waking hours. They called this the glymphatic system, a play on lymphatic, the body's cleanup system, and glial cells, the support cells in your brain. Here's what makes this profound. Among the toxins being flushed out are beta amyloid proteins and tau proteins, the exact substances that build up in the brains of Alzheimer's patients. Every night when you close your eyes, your brain is literally preventing dementia. Let me put this in perspective. Your brain is only 2% of your body weight, but uses 20% of your energy. It's constantly working, constantly producing metabolic waste. If that waste isn't cleared, it accumulates. And we now know from decades of research that chronic sleep deprivation is directly linked to increased risk of Alzheimer's disease, Parkinson's disease, and cognitive decline. A groundbreaking 2019 study from Boston University used advanced brain imaging to watch this cleaning process in real time. They found that during deep sleep, neurons literally coordinate their activity to create pulsing waves of cerebrospinal fluid. It's like your brain is conducting an orchestra of cleanup, and it can only happen when you close your eyes and surrender to sleep. So why? Why would evolution create a system where we have to shut down for hours every day just to clean our brains? Couldn't we have evolved a way to stay awake and clean simultaneously? The answer reveals something profound about how life works. The energy cost of running your conscious mind, processing information, making decisions, reacting to stimuli, is enormous. It's so enormous that your brain literally cannot afford to run the cleanup crew at the same time. You have to shut down the factory to clean the factory. This is why we spend 1/3 of our lives with our eyes closed. Not because we're lazy, not because we're wasting time, but because consciousness itself is so metabolically expensive that we need dedicated offline time just to maintain the machinery that generates it. And here's the beautiful paradox that brings us full circle to those ancient organisms in the primordial ocean. The act of closing your eyes and entering darkness isn't shutting down. It's powering up for tomorrow. Your ancestors 300,000 years ago instinctively knew this. The Egyptians 5,000 years ago built temples to honor this. Buddhist monks 2,500 years ago developed practices to optimize this. And William Dement in the 1950s finally proved this scientifically. Every time you close your eyes at night, you're participating in a ritual as old as life itself. You're connecting to an ancient wisdom written into your DNA. You're allowing your brain to do what it was designed to do: heal, clean, consolidate, and prepare. But this is just the beginning of the story. Because what happens after you close your eyes, the symphony that plays out in your sleeping brain, is even more extraordinary than this ancient gateway we've just walked through. So, you've closed your eyes, you've passed through that ancient gateway, but now, right now, something extraordinary is beginning to happen inside your skull. Your brain is about to perform the most complex symphony in all of biology. And here's what most people get completely wrong. They think your brain is shutting down. Nothing could be further from the truth. Imagine you're at a concert hall. The lights dim, the audience goes quiet, and then the orchestra begins to play. Not one instrument, but dozens, each with its own rhythm, its own melody, yet somehow creating perfect harmony. This is exactly what's happening in your brain the moment you close your eyes. Except instead of violins and cellos, your brain is conducting 86 billion neurons, firing in precise patterns that scientists call brain waves. Let me take you to Chicago, 1924. A German psychiatrist named Hans Berger had just invented something revolutionary: the electroencephalogram, or EEG. For the first time in human history, we could actually see the electrical activity of the brain. Berger placed electrodes on a person's scalp and recorded squiggly lines on paper. When the person was awake with eyes open, the lines were rapid and chaotic, what he called beta waves. But the moment the person closed their eyes and relaxed, something magical happened. The pattern changed. It became rhythmic, like ocean waves. He called them alpha waves. This was the first note in our symphony. Alpha waves oscillate at 8 to 12 cycles per second. When you close your eyes and simply relax, not sleeping yet, just resting, your brain shifts from beta's frantic pace to alpha's gentle rhythm. It's like switching from a rock concert to a meditation chant. In this state, Your brain uses about 20% less energy than when your eyes are open and alert. This alone is remarkable. Just closing your eyes saves your brain significant power. But here's where it gets truly fascinating. A 2018 study from MIT found that these alpha waves aren't random. They're actually your brain's way of inhibiting certain sensory inputs. Think of them as a volume control. When you're bombarded with visual information, which is about 30% of your brain's processing power, alpha waves help dial it down. This is why people instinctively close their eyes when trying to remember something or concentrate deeply. Your brain is saying, okay, turn down the external noise so I can focus on what's inside. Now you drift deeper, your muscles begin to relax, your breathing slows. You're entering what sleep scientists call stage 1 or N1 sleep, the lightest stage of sleep. This is where you encounter theta waves, oscillating at 4 to 8 cycles per second. Even slower, even more rhythmic. This stage lasts only 5 to 10 minutes, but it's crucial. Your brain is transitioning from wakefulness to sleep, like a plane descending through clouds. Here's something remarkable that happens in this theta state. Hypnagogic hallucinations. About 70% of people experience them. You might see random images, hear someone calling your name, or feel like you're falling, that sudden jerk that wakes you up. The scientific term is hypnic jerk, and it happens because your motor system is shutting down at a different rate than your conscious awareness. Your brain is essentially running diagnostics, testing the boundaries between waking and sleeping. Ancient humans probably interpreted these experiences as spiritual, the moment the soul begins to leave the body. We now know it's your brain's orchestra tuning up. But let's pause here because we need to talk about the maestro of this entire symphony, a scientist who changed everything we know about sleep, Matthew Walker. In 2017, Walker published a book called Why We Sleep, and it became a global phenomenon. Not because it was sensational, but because it was terrifying in its clarity. Walker is a professor of neuroscience at UC Berkeley, and he spent over 20 years studying sleep. His central thesis, backed by thousands of studies, is simple and stark. The shorter your sleep, the shorter your life. Walker's research revealed something that shocked even the scientific community. When you sleep less than 7 hours a night, your risk of cardiovascular disease increases by 200%. Your ability to form new memories drops by 40%. Your immune system's effectiveness decreases by 70%. He found that after just one night of sleeping only 4 to 5 hours, your natural killer cells, the immune cells that fight cancer, drop by 70%. One night. This isn't about feeling tired. This is about your body's fundamental defense systems collapsing. But why? Why does the orchestra falling apart in your sleep affect everything else? The answer lies in what happens next as you drift even deeper. Stage 2, sleep, or N2, is where you spend about half of your total sleep time. Your heart rate slows, your body temperature drops, and your brain introduces 2 new patterns: sleep spindles and K-complexes. These sound like science fiction terms, but they're real, measurable phenomena. Sleep spindles are sudden bursts of rapid brain activity that last just a second or two. Scientists discovered in 2013 that these spindles are directly correlated with intelligence, specifically the ability to integrate new information with existing knowledge. The more sleep spindles you produce, the better your brain is at learning. K-complexes are even stranger. They're these sharp, dramatic spikes in brain activity, like lightning strikes in your sleeping brain. For years, scientists didn't know what they were for. Then, in 2011, researchers at Massachusetts General Hospital discovered something incredible. K-complexes are your brain's way of protecting your sleep. When an external noise or stimulus threatens to wake you, a car horn, a door closing, your brain generates a K-complex to suppress that stimulus and keep you asleep. It's like your brain is saying, "No, not now. We're busy down here." Now, we descend into the deepest part of the symphony. Stage 3, also called slow wave sleep or deep sleep. This is where delta waves emerge, the slowest brain waves, oscillating at just 0.5 to 4 cycles per second. Imagine standing on a beach watching massive, slow, ocean swells. That's what your brain looks like on an EEG during deep sleep. These waves are so large and so synchronized that they represent millions of neurons firing in perfect unison. This is the stage where that glymphatic cleaning system we talked about earlier kicks into high gear. But there's something else happening here that's absolutely critical: growth hormone release. During deep sleep, your pituitary gland releases about 70% of your daily growth hormone. This isn't just for children growing taller. In adults, growth hormone repairs muscles, bones, and tissues. It's why athletes who sleep poorly perform worse and get injured more often. Your body is literally rebuilding itself during deep sleep. Here's the tragedy of modern life. As we age, we naturally get less deep sleep. A 20-year-old might spend 20% of the night in deep sleep. A 70-year-old might get less than 5%. This isn't just aging. It's one of the reasons we age. Less deep sleep means less growth hormone, less tissue repair, less glymphatic cleaning. The orchestra is still playing, but it's missing key instruments. But wait, we haven't reached the grand finale yet. After cycling through these stages for about 90 minutes, your brain does something that seemed impossible when scientists first discovered it in 1953. You enter REM sleep, rapid eye movement sleep. And this is where everything we thought we knew about sleep gets turned upside down. Let me take you back to that night in 1953, University of Chicago. Eugene Azarinsky, a graduate student working in Nathaniel Kleitman's lab, was watching his 8-year-old son, Armand, sleep as part of a study. The boy had electrodes attached to his head, and Azarinsky was monitoring the EEG machine in the next room. Suddenly, the needles went crazy. The brain activity looked almost identical to waking activity. Azarinsky thought the machine was broken. He checked. Everything was working fine. His son was definitely asleep, breathing slow, body still, but his brain was lighting up like a Christmas tree. Then he noticed something bizarre. Under the boy's closed eyelids, his eyes were darting back and forth, rapidly, as if watching a tennis match. Azarinsky woke his son and asked, "Were you dreaming?" The boy said yes. He'd been dreaming vividly about climbing mountains. This was the eureka moment. REM sleep and dreaming were connected. The discovery was so significant that it appeared on the front page of the New York Times in 1953. Here's what makes REM sleep paradoxical. Your brain consumes as much energy as when you're awake, sometimes even more. Your neurons are firing rapidly. Your brain is processing information, consolidating memories, making connections between ideas. Meanwhile, your body is completely paralyzed. Every voluntary muscle except your eyes and diaphragm is shut down. This paralysis is called REM atonia, and it's a safety mechanism. Without it, you would physically act out your dreams. Some people have a disorder where this mechanism fails. It's called REM sleep behavior disorder, and they literally punch, kick, and run in their sleep, sometimes injuring themselves or their partners. But why would evolution create a state where your brain is highly active but your body can't move? This seems dangerous. You're vulnerable to predators. You're burning precious calories. There must be a reason. And the reason, as Matthew Walker's research has shown, is that REM sleep is where your brain processes emotions and makes creative connections. In 2009, Walker and his team conducted a fascinating experiment. They showed participants emotionally charged images, photos of car accidents, crying children, violent scenes, and measured their emotional reactions. Then they had half the group take a nap that included REM sleep, while the other half stayed awake. 12 hours later, they showed the same images again. The group that got REM sleep showed significantly reduced emotional reactivity. They could look at the images without the same stress response. It was as if REM sleep had taken the emotional sting out of the memories while preserving the factual content. This is profound. REM sleep is like overnight therapy. It processes your emotional experiences, files away what's useful, and dulls the pain. This is why sleeping on it actually works for emotional problems. Your REM sleep is literally reprocessing the experience, softening the sharp edges. But here's the truly mind-bending part. During REM sleep, your prefrontal cortex, the logical, rational part of your brain, is relatively quiet. Meanwhile, your visual cortex, your motor cortex, and your emotional centers are hyperactive. This creates the bizarre, illogical, emotionally intense quality of dreams. Your brain is making random associations, connecting ideas that would never connect during waking hours. And sometimes, just sometimes, these random connections lead to breakthrough insights. This brings us to one of the most famous stories in the history of science. August Kekulé, a German chemist, was struggling in the 1860s to understand the structure of benzene. He knew the molecular formula, C6H6, but couldn't figure out how the atoms were arranged. One evening, exhausted from work, he dozed off in his chair. In his dream, he saw atoms dancing and forming chains, and then one chain formed a snake that seized its own tail, creating a ring. He woke up with a start. That dream gave him the answer. Benzene is a ring structure. This discovery revolutionized organic chemistry. Was this just luck? Maybe. But here's the thing. Similar stories appear throughout history. Dmitri Mendeleev saw the periodic table in a dream. Elias Howe invented the lock-stitch sewing machine after dreaming about spears with holes in their tips. Paul McCartney heard the entire melody for Yesterday in a dream. Your brain during REM sleep is exploring solution spaces it would never explore while awake. Now, let me contrast this with what happens when you don't let the orchestra play. In 2007, researchers at Harvard Medical School did a cruel but illuminating experiment. They taught participants a complex finger-tapping sequence, like learning a piano piece, and then prevented some of them from entering REM sleep. They could sleep, but the moment the EEG showed RM patterns, they were gently woken. The next day, the RM-deprived group showed minimal improvement in the task. The group that got normal sleep improved by 20%. The same amount of practice time, but RM sleep made all the difference. This is why pulling an all-nighter before an exam is one of the worst strategies possible. You might feel like you're gaining study time, but you're losing the very mechanism that consolidates that study into long-term memory. The symphony needs to play the whole composition, not just the opening notes. Here's the complete picture of what a normal night looks like. You cycle through these stages: light sleep, deep sleep, REM sleep, about 4 to 6 times per night, each cycle lasting roughly 90 minutes. The first half of the night is rich in deep sleep. The second half is rich in REM sleep. This is why waking up after just 4 hours feels so much worse than waking after 7 or 8. You've gotten the deep sleep cleaning, but you've missed most of the REM sleep emotional processing and memory consolidation. The most common mistake people make is thinking they can catch up on sleep on weekends. I'll sleep 5 hours on weekdays and 10 hours on Saturday. But sleep doesn't work like a bank account. You can't go into debt and then make a deposit. The damage from sleep deprivation happens in real time. Each night you short yourself, your brain misses that specific night's symphony. The performance can't be replayed later. And here's something that should change how we think about productivity. Your brain during sleep is not idle. It's not wasting time. When you close your eyes and let the orchestra play, alpha waves, theta waves, delta waves, sleep spindles, K-complexes, and the wild creative chaos of REM, your brain is doing work that it literally cannot do while you're awake. The brain waves we've mapped are not just background noise. They're functional. They're purposeful. They're essential. Think about it this way. During waking hours, your brain is like a busy office where everyone is taking meetings, answering emails, putting out fires. There's no time for deep thinking, for strategic planning, for organizing the file cabinets. Sleep is when everyone goes home and the night crew comes in. They clean, they organize, they file away the important documents, they shred what's no longer needed, they repair broken equipment. In the morning, the day crew returns to an office that functions smoothly, not because nothing happened overnight, but because critical maintenance happened. This is the symphony of darkness, 5 distinct movements: alpha, theta, deep sleep, REM, and the transitions between them, each with its own tempo, its own purpose, its own contribution to the whole. Hans Berger's discovery in 1924 was just the first glimpse. Eugene Oserinsky's REM discovery in 1953 opened the door wider. Matthew Walker's research in the 21st century has shown us just how high the stakes are. Your brain is not resting during sleep, it's performing. It's conducting an orchestra of 86 billion neurons in the most complex symphony in nature. And every single night that you don't let that symphony play in full, every night you cut it short, interrupt it, or try to skip it, you're silencing instruments that are essential to your health, your memory, your emotions, and your very life. The question we haven't answered yet is, what exactly is being cleaned, consolidated, and processed during this nightly performance? What are the specific toxins being flushed out? What memories are being preserved and which are being discarded? And perhaps most importantly, what happens when the cleaning crew doesn't show up night after night after night? Right now, at this very moment, there's a janitor working inside your skull. And if that janitor doesn't show up for work tonight, or any night, the consequences won't show up immediately. They'll show up 20 years from now, when you can't remember your grandchildren's names, when you can't find your way home from the grocery store, when the lights slowly dim in your mind and never turn back on. Picture this. You're in a massive office building. Hundreds of people work there every day, generating paperwork, coffee cups, trash, spills. Now, imagine that building never hired a cleaning crew. What happens after a week, after a month, after a year? The building becomes unusable, toxic, dangerous. This is exactly what happens to your brain when you chronically deprive it of sleep. And the terrifying part is, you won't feel it happening until it's too late. I want to dive deep into one of the most important discoveries in neuroscience in the last decade. A discovery so profound that it fundamentally changed how we understand brain health, aging, and diseases like Alzheimer's. We touched on this briefly, but now we need to understand the full picture of what's really happening inside your head every single night. And I promise you, by the end of this section, you will never think about staying up late the same way again. If you're finding this information valuable, hit that like button. It helps more people discover this crucial knowledge. And if you haven't subscribed yet, this is the perfect time because we're only going deeper from here. Let's go back to Rochester, New York, 2012. Dr. Macon Nedergaard's laboratory at the University of Rochester Medical Center. Well, Nedergaard is a Danish neuroscientist who had been studying glial cells, the support cells in the brain that for decades were thought to just be structural scaffolding for neurons. Scientists called them glue cells because they seemed to just hold everything together, but Nedergaard suspected they did something more. She was working with mice using a revolutionary technique called two-photon microscopy that allowed her to watch a living brain in real time. She injected fluorescent dyes into the cerebrospinal fluid surrounding the brain and watched what happened. When the mice were awake, the dye barely moved. It stayed mostly in the fluid spaces around the brain, but when the mice fell asleep, something extraordinary happened. The dye began flowing rapidly into the brain tissue itself, washing through the spaces between cells like a river after a dam breaks. The flow was powerful, organized, purposeful. Nedergaard watched in real time as cerebrospinal fluid, the clear liquid that cushions your brain and spine, was being pumped through brain tissue, picking up waste products and flushing them out into the lymphatic vessels in the neck. It was a complete waste removal system, and it operated almost exclusively during sleep. She published her findings in the journal Science in 2013, and the paper sent shockwaves through neuroscience. Here's why. For over a century, scientists had a puzzle. Every organ in your body has a lymphatic system, a network of vessels that removes waste products and toxins. Your liver, kidneys, muscles, skin, all have lymphatic vessels, but the brain doesn't. There are no lymphatic vessels inside your brain. So how does the brain, which generates enormous amounts of metabolic waste, get rid of that waste? The answer was hiding in plain sight. It uses sleep. Nadergaard named this system the glymphatic system, a combination of glial cells and lymphatic system. Here's how it works at the molecular level, and this is where it gets fascinating. Your brain has these specialized channels called aquaporin 4 water channels, located on the feet of astrocytes, a type of glial cell. During sleep, these channels open wide, allowing cerebrospinal fluid to flood into the brain at 10 to 20 times the rate it does during waking hours. But here's the critical part. For this to work, your brain cells need to physically shrink. We now know from precise measurements that during deep sleep, the extracellular space, the space between your brain cells, expands by about 60%. Your neurons and glial cells literally contract, creating highways for the cerebrospinal fluid to flow through. It's like your brain is a crowded city during the day, and at night, everyone goes home, creating empty streets for the garbage trucks to efficiently collect trash. Now, what exactly is this trash? This is where the story gets deeply personal and urgent. Among the waste products being flushed out are two proteins that you need to know about: beta amyloid and tau. These aren't just random waste. They're the primary culprits in Alzheimer's disease. Let me explain what these proteins do. Beta amyloid is a sticky protein fragment that your brain produces naturally every single day as a byproduct of normal neural activity. In a healthy brain that gets adequate sleep, beta amyloid is cleared out each night before it can accumulate. But when you don't sleep enough, beta amyloid starts to build up. And here's the vicious cycle. Beta amyloid buildup makes it harder to get deep sleep. Less deep sleep means less cleaning. Less cleaning means more buildup. It's a spiral that, once it starts, is incredibly difficult to stop. Tau protein is even more sinister. Normally, tau helps stabilize the internal structure of neurons. Think of it like scaffolding inside a building. But when tau becomes abnormal, it forms tangles inside neurons, essentially strangling them from the inside. These tau tangles spread from cell to cell like an infection, killing neurons as they go. And sleep is the only time your brain can effectively clear out this toxic tau before it tangles. In 2018, researchers at Washington University in St. Louis published a landmark study. They kept healthy young adults awake for just one night and measured their beta amyloid levels using PET scans. After a single night of sleep deprivation, beta amyloid levels in their brains increased by 5%. One night. Then they looked at people who chronically slept poorly, defined as less than 6 hours per night or frequently interrupted sleep. These people had 30% higher levels of beta amyloid in their brains compared to good sleepers of the same age. Think about what this means. If you're in your 30s or 40s right now, and you're regularly sleeping 5 or 6 hours a night because you're grinding at work, building a business, binge-watching shows, or scrolling through your phone, you're not just tired, you're actively measurably accumulating the proteins that cause Alzheimer's disease. The disease that will steal your memories 30 years from now is being seeded right now by your sleep choices today. Let me give you 2 case studies that illustrate this with haunting clarity. Margaret Thatcher, the former Prime Minister of the United Kingdom, was famous for sleeping only 4 to 5 hours a night. She wore it as a badge of honor, claiming that sleep is for the weak. She governed Britain for 11 years, running on minimal sleep. In her later years, she developed severe dementia. By the time she died in 2013 at age 87, she couldn't recognize her own daughter. Her final years were marked by confusion, memory loss, and cognitive decline. We can't prove that her sleep deprivation caused her dementia. Correlation isn't causation. But her story fits perfectly with what we now know about sleep and brain health. Compare this to Thomas Edison, the famous inventor who also bragged about sleeping only 3 to 4 hours a night. Edison believed that sleep was a waste of time and that the electric light bulb he invented would eventually eliminate the need for sleep altogether. He lived to be 84, but his later years were marked by memory problems and what his family described as periods of confusion and irritability. Again, we can't prove direct causation, but the pattern is striking. Now contrast these stories with modern scientific evidence. In 2020, researchers at UC Berkeley published a study that tracked 32,000 people over 25 years. They found that people who averaged 7 to 8 hours of sleep per night had the lowest risk of dementia. Those who consistently slept less than 6 hours had a 30% higher risk. Those who slept less than 5 hours had nearly double the risk. The relationship was clear, dose-dependent, and terrifying. But it's not just Alzheimer's. In 2019, a study in the journal Neurology found that poor sleep quality in midlife is associated with increased risk of Parkinson's disease decades later. The mechanism appears to be similar: alpha-synuclein, a protein that accumulates in Parkinson's disease, is normally cleared during sleep. Without adequate sleep, it builds up in the brain regions that control movement, eventually causing the tremors and rigidity characteristic of Parkinson's. Here's what's truly frightening: the damage is silent. You can't feel proteins accumulating in your brain. There's no pain signal, no warning light. Beta amyloid starts building up 15 to 20 years before the first symptoms of Alzheimer's appear. By the time you notice memory problems, the damage is already extensive. It's like termites eating the foundation of your house. You don't see the problem until the house is already structurally compromised. Let me give you the timeline of what happens with chronic sleep deprivation. After 1 week of sleeping 6 hours or less per night, your genes for immune function start to turn off while genes for inflammation turn on. After 2 weeks, your insulin sensitivity, your body's ability to regulate blood sugar, drops by 30%, putting you in a pre-diabetic state. After 1 month, the hippocampus, your brain's memory center, starts to show measurable shrinkage on MRI scans. After 6 months to a year, beta amyloid deposits become visible on specialized brain scans. This is the invisible countdown happening in millions of people who think they're just pushing through with less sleep. Now, let's talk about something that makes this even worse: circadian misalignment. Your glymphatic system doesn't just need sleep, it needs sleep at the right time. There's a reason humans evolved to sleep at night. Your body has a master clock in a tiny region of your brain called the suprachiasmatic nucleus. This clock coordinates thousands of biological processes, including when your glymphatic system operates most efficiently. A 2017 study from the University of Surrey in the UK found that shift workers, people who work night shifts and sleep during the day, have significantly impaired glymphatic function compared to day workers, even when they get the same total amount of sleep. Why? Because sleeping during the day, when your circadian clock expects you to be awake, reduces the efficiency of waste clearance. The cleaning crew shows up, but they're working against the biological clock, making them less effective. This has massive implications. There are approximately 15 million shift workers in the United States alone. Healthcare workers, police officers, firefighters, factory workers, truck drivers, all working against their circadian rhythms. Studies have found that long-term shift workers have a 50% higher risk of developing neurological diseases compared to day workers. We're asking millions of people to sacrifice their brain health for economic productivity. Here's a common mistake people make. They think they can catch up on brain cleaning during the weekend. I'll sleep 5 hours Monday through Friday and 10 hours on Saturday and Sunday. But the glymphatic system doesn't work that way. Each night of inadequate sleep is a missed opportunity for cleaning that cannot be fully recovered. It's like missing dental hygiene. If you don't brush your teeth for 5 days, brushing really well on the weekend doesn't undo the 5 days of plaque buildup. Another critical mistake, relying on alcohol to help you sleep. Yes, alcohol makes you drowsy and helps you fall asleep faster, but alcohol suppresses REM sleep and reduces the efficiency of glymphatic clearance. A 2015 study found that people who consumed alcohol within 4 hours of bedtime had 40% less effective waste clearance during sleep compared to nights without alcohol. You might be sleeping, but your brain isn't properly cleaning. The same goes for sleeping pills. Many common sleep medications like Ambien or Benadryl don't produce natural sleep architecture. They knock you unconscious, but your brain doesn't cycle through the proper stages of sleep, and glymphatic function is impaired. You wake up feeling groggy not just because of the drug's hangover effect, but because your brain didn't properly clean itself during the night. So, what can we do? The first step is acknowledging that sleep isn't optional luxury, it's biological necessity. The second step is understanding that protecting your sleep means protecting your future cognitive health. Every night you prioritize sleep, you're investing in your brain 20, 30, 40 years from now. Nadergaard's discovery of the glymphatic system was nominated for the Nobel Prize, and for good reason. She revealed a fundamental mechanism that explains why every animal that has a brain also sleeps. The brain, despite being only 2% of your body weight, produces 25% of your body's waste. That waste has to go somewhere, and the only efficient way to remove it is during sleep, when the brain can physically expand its waste clearance highways. Think about the elegance of this system. Your brain can't clean itself while you're awake because the neural activity required for consciousness, processing information, making decisions, moving your body, generates the very waste that needs to be cleared. It would be like trying to clean a factory while the assembly line is running at full speed. The factory has to shut down for cleaning to be effective. Your brain has to power down into sleep for the janitors to do their work. This is why evolution preserves sleep despite its apparent vulnerability. Being unconscious for 8 hours seems dangerous from a survival perspective. You can't watch for predators, you can't forage for food, you can't reproduce. Yet every animal with a complex nervous system sleeps. Why? Because the alternative, a brain clogged with toxic waste, is even more dangerous. A brain that doesn't sleep is a brain that slowly poisons itself. The most profound lesson from all of this is that your brain health isn't just about what you do when you're awake. It's not just about eating well, exercising, or staying mentally active, though those things matter. Your brain health is equally, if not more, about what you do when you close your eyes, about giving your brain permission to shrink its cells, open its aquaporin channels, and flood itself with cleansing cerebrospinal fluid, about trusting that the midnight janitor knows what to do. Margaret Thatcher and Thomas Edison saw sleep as weakness. Modern hustle culture often echoes this sentiment. But they were wrong. Sleep isn't weakness, it's wisdom encoded in billions of years of evolution. It's your brain's way of saying, I need to take out the trash before it accumulates into something deadly. The proteins accumulating in your brain right now aren't abstract concepts. They're physical molecules with real consequences. And every night that you shortchange your sleep, you're allowing those proteins to build up, one molecule at a time, like snow accumulating on a mountain slope. Eventually, that snow becomes an avalanche. But here's the hopeful part. It's never too late to start protecting your brain. Studies show that improving sleep quality, even later in life, can slow cognitive decline. Your glymphatic system is ready to work. It just needs you to give it the time and conditions to do its job. So, the cleaning crew is standing by, mops and buckets ready. The question is, will you let them in tonight? Will you close your eyes, silence your devices, darken your room, and give your brain the 7 to 9 hours it needs to flush out the toxins, clear the debris, and reset for another day of thinking, feeling, and being fully human. Because what we haven't explored yet is what your brain does with all that cleaning and maintenance. Once the slate is wiped clean, once the toxic proteins are flushed away, what happens to all the experiences, lessons, and moments from your day? Where do they go? How does your brain decide what to keep and what to discard? Imagine you studied for 8 hours straight for the most important exam of your life. You memorized every fact, every formula, every concept. You went to bed feeling confident. And when you woke up, you knew 30% more than when your head hit the pillow without opening a single book. This isn't magic. This isn't a study hack. This is your brain doing something so sophisticated that we're only beginning to understand it. And the tragic irony is that millions of students do exactly the opposite, pulling all-nighters and destroying the very mechanism that would help them succeed. Your brain has a library, not a metaphorical library, an actual physical structure that stores every significant experience you've ever had. And every night when you close your eyes, a team of invisible librarians goes to work, sorting through the day's experiences, deciding what goes on the permanent shelves and what gets thrown in the recycling bin. This process is so critical that without it, you would wake up every morning as if you were meeting yourself for the first time. And understanding how this works might be the most practical knowledge you gain about sleep. If this exploration into how your brain builds and preserves who you are resonates with you, take a second to hit that like button. It helps this content reach people who need to understand that their memories, their very identity, depends on what happens when they close their eyes. And if you're not subscribed yet, join us, because we're about to reveal how your sleeping brain is quite literally writing the story of your life. Let me take you to Harvard Medical School, 2000. Dr. Robert Stick Gold, a cognitive neuroscientist, designed an elegantly simple experiment that would revolutionize how we think about learning and memory. He had participants play Tetris, yes, the falling blocks video game, for several hours. It was a task that required both visual spatial skills and pattern recognition. Some participants were complete novices who'd never played before. He divided them into 2 groups. One group was allowed to sleep normally that night. The other was kept awake. The next day, both groups played Tetris again. The sleep group showed dramatic improvement. They were faster, made fewer errors, and achieved higher scores. The sleep-deprived group showed minimal improvement despite having the same practice time. But here's where it gets fascinating. Several participants in the sleep group reported something strange. They dreamed about Tetris, not elaborate stories involving Tetris pieces, just abstract images of falling blocks, rotating shapes, the visual patterns of the game. Stick Gold realized he was watching memory consolidation in action. The brain was replaying and strengthening the neural patterns associated with the task. The dreams were the visible surface of a much deeper process happening beneath consciousness. But the most remarkable finding came from the novice players. Those who had never played Tetris before and dreamed about it showed the greatest improvement. Their brains were working overtime during sleep to integrate this completely new skill into their existing neural networks. Stick Gold called this sleep-dependent memory consolidation, and it opened up an entirely new field of research. To understand what's really happening, we need to talk about the hippocampus. This seahorse-shaped structure, about the size of your thumb, sits deep in your brain's temporal lobe. You have 2 of them, one in each hemisphere. And these 2 small structures are arguably the most important real estate in your entire nervous system. The hippocampus is your brain's temporary storage facility. During the day, as you experience life, learning new names, navigating to new places, absorbing information, all of that gets temporarily encoded in your hippocampus. Think of it as a notepad, where your brain jots down rough drafts. But the hippocampus has limited capacity. It can't store everything forever. This is where sleep becomes crucial. Here's the process that unfolds every night. During slow-wave sleep, that deep sleep we talked about earlier, your hippocampus begins replaying the day's experiences to your neocortex, the outer layer of your brain where long-term memories are stored. This isn't a simple transfer like copying files from a USB drive to a hard drive. It's a creative process. Your brain is deciding which memories are important enough to keep, which details to preserve, and how to integrate new information with existing knowledge. A groundbreaking 2007 study from the University of Liège in Belgium actually captured this process in action. They had people learn a complex finger-tapping sequence, like learning a difficult piano piece. During sleep that night, researchers used fMRI scans to watch the participants' brains. What they saw was extraordinary. The exact same brain regions that were active during learning lit up again during sleep, but in a specific pattern. First, activity in the hippocampus. Then, milliseconds later, activity in the motor cortex. The hippocampus was teaching the motor cortex, transferring the skill from temporary storage to permanent storage. But here's what makes this profound. The replay wasn't happening once or twice. It was happening hundreds of times throughout the night, each repetition strengthening the neural connections. Your brain was essentially practicing the skill while your body was paralyzed in sleep. This is why musicians, athletes, and surgeons who get adequate sleep after intensive practice sessions show dramatically better performance than those who don't. Their brains are rehearsing while they sleep. Let me give you a real-world example that illustrates this perfectly. In 2002, researchers at the University of Chicago worked with medical students learning to perform a laparoscopic surgery procedure, a delicate operation requiring precise hand-eye coordination. They divided students into two groups. One practiced the procedure and then slept normally. The other practiced and stayed awake. 2 days later, both groups performed the surgery again. The well-rested group made 30% fewer errors and completed the procedure 20% faster. Lives could literally depend on whether a surgeon slept well during their training. But here's where we need to distinguish between different types of memory because your brain treats them differently during sleep. There are two main categories: declarative memory and procedural memory. Declarative memory is what you know, facts, events, information. The capital of France is Paris. I had breakfast this morning. These are things you can consciously recall and declare. Procedural memory is how you know, skills, habits, unconscious knowledge. How to ride a bike, how to type without looking at the keyboard, how to play a musical instrument. Those two types of memory consolidate during different stages of sleep. Declarative memories, your facts and experiences, consolidate primarily during slow-wave sleep in the first half of the night. This is when your hippocampus is actively transferring information to your neocortex. Procedural memories, your skills and habits, consolidate primarily during REM sleep in the second half of the night. This is when your motor cortex and cerebellum are being reprogrammed. This has massive implications for how you should approach learning. If you're studying for a history exam, declarative memory, the most important thing is to get the first half of the night's sleep when slow-wave sleep dominates. If you're learning to play guitar, procedural memory, the second half of the night, rich in REM sleep, is crucial. This is why sleep deprivation destroys learning, regardless of the type. You need both halves of the night for complete memory consolidation. Now, let me tell you one of the most famous stories in the history of science, a story that perfectly illustrates the creative power of sleep. August Kekulé was a German chemist working in the 1860s. He was obsessed with understanding the molecular structure of benzene, a common chemical compound. He knew the molecular formula, 6 carbon atoms and 6 hydrogen atoms, but couldn't figure out how they were arranged. For months, he tried every configuration he could think of. Linear chains, branching structures, nothing worked. The math didn't add up. The chemical properties didn't match his predictions. He was stuck, frustrated, intellectually exhausted. One evening in 1865, after another long day of failed attempts, Kekulé dozed off in his chair in front of the fireplace. In his dream, he saw atoms dancing before his eyes. They formed chains, twisted and turned like snakes. Then, one of the snakes seized its own tail, forming a perfect ring. Kekulé jolted awake. That was it. Benzene wasn't a chain, it was a ring. A perfect hexagon of carbon atoms with hydrogen atoms attached. He spent the rest of the night testing this structure mathematically, and everything fit. The ring structure of benzene explained all of its chemical properties. This discovery revolutionized organic chemistry. The benzene ring became one of the most important structures in chemistry, fundamental to understanding everything from plastics to pharmaceuticals to DNA. Kekulé's dream literally changed the course of science. But this wasn't divine inspiration or mystical revelation. This was his sleeping brain doing exactly what sleep is designed to do, making novel connections between pieces of information that his conscious logical mind couldn't connect. During waking hours, your prefrontal cortex, the logical, analytical part of your brain, dominates. It's excellent at focused, linear thinking, but it's also conservative. It tends to think within existing frameworks, following known rules and patterns. During REM sleep, the prefrontal cortex quiets down, and other brain regions, visual cortex, motor cortex, memory centers, become hyperactive. Without the prefrontal cortex's strict oversight, these regions can make wild, seemingly random associations. Most of these associations are nonsense. This is why most dreams are bizarre and illogical. But occasionally, very occasionally, a random association is actually a breakthrough insight. Your sleeping brain connects two pieces of information that your waking brain kept separated. And when you wake up, you have a solution to a problem that seemed unsolvable. This isn't just anecdotal. In 2004, researchers at the University of Lübeck in Germany designed a clever experiment to test whether sleep could produce creative insights. They gave participants a complex mathematical task that had a hidden shortcut. If you figured out the trick, you could solve the problems much faster. But the trick was very difficult to discover through conscious effort. They divided participants into 3 groups: those who worked on the problem and then slept, those who worked and stayed awake, and those who worked and then came back fresh without practice. The results were stunning. In the group that slept, 60% discovered the hidden shortcut when they returned to the task. In the groups that stayed awake or took a break, only 25% figured it out. Sleep didn't just help them remember the problem, it helped them solve it. This phenomenon has been documented throughout history. Dmitri Mendeleev, the Russian chemist, saw the entire periodic table of elements in a dream in 1869. He woke up, wrote it down, and according to his own account, only one element needed to be corrected. Elias Howe, inventor of the lock-stitch sewing machine, was stuck on a crucial design problem. In a dream, he was captured by natives who threatened him with spears that had holes near their tips. He woke up realizing the solution. The needle should have the hole near its point, not at the base. This single insight made the modern sewing machine possible. Paul McCartney famously heard the entire melody for "Yesterday," one of the most famous songs in history, in a dream. He woke up and immediately went to the piano to play it before he forgot. He was so convinced he must have unconsciously plagiarized it that he spent weeks playing it for other musicians, asking if they had heard it before. They hadn't. His sleeping brain had composed one of the most commercially successful songs ever recorded. Now, I need to address a common misconception that has serious consequences for students worldwide. Many people believe that if you study right up until the moment you need to perform, cramming all night before an exam, you'll retain more information because it's fresh in your mind. This is catastrophically wrong. In 2008, researchers at UC Berkeley compared 2 groups of students. Both studied the same material for the same amount of time. One group studied in the evening and then slept before the test. The other studied in the morning, stayed awake all day, and took the test in the evening. The evening study group, the ones who slept, scored an average of 35% higher. Same study time, dramatically different results. The only variable was sleep. Here's why. Without sleep, the information stays trapped in your hippocampus. It's like writing notes that you never file away. You can access them in the short term, but they're fragile, easily disrupted, and won't be there when you need them later. With sleep, the information gets transferred to your neocortex, integrated with existing knowledge, and becomes stable, long-term memory that you can access reliably. The tragedy is that students often do exactly the opposite. They sacrifice sleep to study more, not realizing they're destroying the very mechanism that would make their studying effective. It's like buying a high-performance car but never putting oil in the engine. Eventually, the engine seizes up, and the car becomes useless. Without sleep, your learning becomes useless. Let me give you the practical application of all this research. If you're learning something new, whether it's a language, a musical instrument, a sport, or studying for an exam, here's the optimal strategy. Study or practice intensively, but end your session at least 30 minutes before you plan to sleep. During those 30 minutes, do something relaxing but engaging, light reading, a walk, conversation. This allows your brain to begin the initial processing without being overwhelmed by new information. Then sleep for at least 7 to 8 hours. Don't set an alarm if possible. Let your brain complete its full consolidation cycles. When you wake up, review the material briefly. You'll be amazed at how much more solid the information feels, how much more automatic the skills seem. This review after sleep is like developing a photograph. It brings out the details that were captured, but not yet visible. Multiple studies have confirmed what's called the sleep on it effect. When people are given a problem and told to sleep on it, they perform significantly better than those told to take your time or think carefully. The phrase itself is ancient wisdom, validated by modern neuroscience. Your sleeping brain is not idle. It's your most sophisticated problem-solving machine. But here's something that should fundamentally change how we structure education. Most schools start early in the morning, forcing teenagers to wake up during their natural sleep window. Adolescents have a biological shift in their circadian rhythm that makes them naturally want to stay up later and sleep later. We're forcing them to learn during hours when their hippocampus is still in sleep mode, when memory consolidation from the previous night isn't complete. Studies have shown that schools that start just 1 hour later see dramatic improvements in academic performance, attendance, and student well-being. In 2018, a large study in Seattle found that when high school start times moved from 7:50 a.m. to 8:45 a.m., median grades increased by 4.5%, and the number of students getting adequate sleep jumped by 34%. We're literally sacrificing our children's learning potential and mental health to accommodate scheduling convenience. The same principle applies to adults. If you're learning a new skill for your career, taking a course, or trying to master new software, the hours you spend learning are only half the equation. The quality of your sleep afterward is the other half. Companies that understand this see it in their training outcomes. Google, Microsoft, and other innovative companies have actually installed nap pods and encourage employees to rest after intensive learning sessions. They've realized that sleep isn't laziness, it's how humans upgrade their mental software. Now, there's one more aspect of memory and sleep that we need to explore, one that has profound implications for who you are as a person. Not all memories are treated equally during sleep. Your brain has to decide what to keep and what to discard. And the selection process reveals something deep about how your identity is constructed. Research has shown that emotionally significant experiences are preferentially consolidated during sleep. A 2007 study found that people who learned lists of emotional words like love, death, fear, joy, retained 15% more of those words after sleep compared to neutral words. Your brain prioritizes memories that have emotional weight. This makes evolutionary sense. Remembering which berries made you sick is more important than remembering the color of the sky that day. But this also means that your sleeping brain is literally choosing which version of you to preserve. Every night, it's making decisions about which experiences define you, which moments are worth keeping, which skills deserve permanent storage. You are, in a very real sense, the sum of your consolidated memories. And sleep is the editor writing your autobiography. Think about that. The person you are when you wake up is slightly different from the person who went to sleep. New memories have been integrated. New skills have been solidified. New connections have been made between disparate pieces of knowledge. Sleep isn't just rest, it's transformation, it's growth. It's the process by which experience becomes wisdom. So, when students pull all-nighters, they're not just risking poor test performance, they're delaying their own development. When professionals sacrifice sleep to appear more dedicated, they're actually becoming less competent. When we glorify lack of sleep as a sign of commitment, we're celebrating self-sabotage. Your brain spent millions of years evolving this sophisticated system for taking the chaos of daily experience and transforming it into organized, accessible knowledge. The hippocampus, with its remarkable ability to temporarily hold everything, working in concert with the neocortex during sleep to build permanent libraries of who you are and what you know. This is not a luxury system. This is not something you can optimize away or replace with coffee and determination. Every night, invisible librarians are working in the memory palace of your mind, cataloging the day's experiences, deciding what belongs in the archives and what can be forgotten. They work in the darkness, in the silence, while you dream. And when you wake, you are someone slightly new, more skilled, more knowledgeable, more you than you were yesterday. But memories and skills are only part of the story. Because there's another dimension to what happens when you close your eyes at night, a dimension that might be even more critical to your well-being, even more fundamental to your ability to function as a human being. Have you ever noticed that the problem that felt overwhelming at 11 p.m. somehow feels manageable at 7 a.m.? That the argument that made you furious last night doesn't seem worth the energy this morning? That the anxiety spiraling out of control before bed has mysteriously quieted by the time you wake up? This isn't positive thinking. This isn't time healing wounds. This is your brain performing emotional surgery while you sleep, literally rewiring your response to yesterday's experiences. Here's something that should terrify you. After just one night of sleeping only 4 hours, the emotional centers of your brain become 60% more reactive to negative stimuli. 60%. One night. You're not just tired, you're emotionally unstable at a neurological level. And in a world where we're constantly told to power through on less sleep, we're creating a population that's chemically, biologically primed for emotional chaos. If you've ever felt like your emotions were more stable after a good night's sleep, or if you've experienced the emotional roller coaster of sleep deprivation, this section will reveal the science behind what you've felt. Hit that like button if you're ready to understand why sleep might be the most powerful emotional therapy we have. And subscribe if you want to keep exploring how your brain and body work in ways that most people never learn about. Because what we're about to uncover could change how you think about managing stress, anxiety, and emotional well-being. Let me take you inside one of the most important structures in your emotional brain, the amygdala. This almond-shaped cluster of neurons, about the size of a walnut, sits deep in your temporal lobe, one on each side of your brain. For decades, neuroscientists called it the fear center. But that's far too simplistic. The amygdala is your emotional significance detector. It tags experiences with emotional weight, determining what matters, what's threatening, what needs your attention. When something startles you, a loud noise, a sudden movement, a disturbing image, your amygdala lights up before your conscious mind even registers what happened. It's triggering your fight or flight response. releasing stress hormones, preparing your body to react. This was incredibly useful when threats were physical and immediate: a predator, a falling rock, a hostile rival. But in the modern world, where most threats are social and psychological, an overactive amygdala becomes a liability. And here's where sleep comes in. In 2007, researchers at UC Berkeley and Harvard Medical School conducted a landmark study that revealed something stunning about what sleep does to your emotional brain. They took two groups of healthy adults and showed them disturbing images: photos of mutilated bodies, severe injuries, violent scenes designed to provoke strong negative reactions. They measured brain activity using fMRI scanners. One group viewed the images after a normal night of sleep. The other group was kept awake for 35 hours straight and then shown the same images. The difference was shocking. In the sleep-deprived group, the amygdala showed 60% more activity in response to the negative images. But here's what's even more remarkable. The connection between the prefrontal cortex, your rational regulating brain, and the amygdala was severed. The prefrontal cortex normally acts like a brake on the amygdala, saying, "Calm down, assess the situation rationally." Without sleep, that brake fails. Your emotional brain is screaming while your rational brain can't be heard. This explains so much about human behavior: why exhausted parents lose their temper over minor things, why sleep-deprived soldiers make poor decisions in combat, why doctors and nurses working 24-hour shifts have higher rates of medical errors, not just because of impaired cognitive function, but because they're emotionally dysregulated. Their amygdalas are hyperactive, their prefrontal cortexes are offline, and they're making decisions in an emotionally compromised state. But the genius of sleep isn't just in preventing emotional hyperactivity, it's in actively healing emotional wounds. Let me tell you about one of the most elegant experiments in sleep science. In 2011, Matthew Walker's team at UC Berkeley, yes, him again, because his work is fundamental to understanding sleep, conducted a study that revealed exactly how sleep processes emotions. They had participants view emotionally charged images in the evening while their brain activity was monitored. Then half the group slept normally while half stayed awake. 12 hours later, they showed the same images again. In the group that slept, something remarkable had happened. The amygdala showed significantly reduced reactivity to the images. The emotional charge had been taken out of the memories. But, and this is crucial, they could still remember the images perfectly. The factual content was preserved, while the emotional sting was removed. Walker called this overnight therapy. During REM sleep specifically, your brain is replaying emotional experiences, but in a unique neurochemical environment. During REM, there's one neurotransmitter that's almost completely absent: noradrenaline, also called norepinephrine. This is your brain's stress chemical. It's what makes your heart race, your palms sweat, your body tense. Every other stage of sleep has noradrenaline present. Only REM sleep is noradrenaline free. So, what's happening is brilliant. Your brain is reactivating the emotional memories, replaying the difficult conversation, the stressful meeting, the embarrassing moment, but without the stress chemistry. It's like watching a movie of a traumatic event instead of experiencing it directly. You can process what happened, understand it, learn from it, but you're not re-traumatized by it. The memory is being reprocessed and filed away, with its emotional intensity reduced. This is why ancient wisdom across cultures has always said, sleep on it when facing emotional turmoil. Your grandmother telling you things will look better in the morning wasn't just optimism, it was neuroscientifically accurate advice. Your brain needs to run the emotional experiences through REM sleep to properly process them. Now, let's talk about the master controller of your sleep and emotional regulation, your circadian rhythm. This 24-hour biological clock governs far more than just when you feel sleepy. It controls the timing of hormone release, body temperature, digestion, and critically, your emotional resilience throughout the day. At the center of this system are two hormones you've probably heard of but may not fully understand: cortisol and melatonin. Let me explain how these work together and why disrupting their natural rhythm creates emotional chaos. Cortisol gets a bad reputation as the stress hormone, but that's unfair. Cortisol is actually essential for waking up and feeling alert. In a healthy circadian rhythm, cortisol levels are highest in the early morning, peaking about 30 minutes after you wake up. This is called the cortisol awakening response. It gives you energy, sharpens your focus, and prepares your body for the day. Throughout the day, cortisol gradually declines, reaching its lowest point around midnight. Melatonin works in opposition. As darkness falls and cortisol drops, your pineal gland, a tiny pine cone-shaped structure in your brain, begins secreting melatonin. Melatonin levels rise throughout the evening, peak around 2 to 3 a.m., and then decline toward morning. Melatonin doesn't knock you unconscious like a sleeping pill. Instead, it signals to your entire body it's nighttime, time to rest, repair, and restore. This rise and fall of cortisol and melatonin is your body's natural rhythm, synchronized with the Earth's rotation. This isn't just about sleep, it's about emotional stability. When cortisol is high at the right time, morning, you feel energized but stable. When it's high at the wrong time, late night, you feel anxious, wired, unable to relax. When melatonin rises naturally in the evening, you feel calm, peaceful, ready for rest. When it's suppressed, you feel restless and emotionally brittle. Here's where modern life creates a perfect storm of emotional dysregulation. In 2002, researchers at Brigham and Women's Hospital in Boston conducted a groundbreaking study on the effects of light on melatonin and mood. They exposed participants to different wavelengths of light in the evening. Blue light, the type emitted by phones, tablets, laptops, and LED lights, was devastatingly effective at suppressing melatonin. Just 2 hours of evening screen time reduced melatonin levels by 22%. And the effects lasted. Melatonin suppression continued even after the light exposure stopped. Think about what this means. When you're scrolling through your phone before bed, you're not just staying awake longer, you're actively suppressing the hormone that helps regulate your emotional state. You're keeping cortisol elevated when it should be dropping. You're disrupting the natural rhythm that took millions of years to evolve. And the consequence isn't just poor sleep, it's emotional instability. A 2017 study published in the journal Sleep Health tracked 5,000 adolescents and their technology use before bed. Those who used screens within 1 hour of bedtime had significantly higher rates of anxiety, depression, and emotional outbursts compared to those who stopped screen time at least 2 hours before bed. The researchers could actually measure the relationship. Each additional hour of evening screen time correlated with a 9% increase in emotional difficulties. This isn't correlation, this is mechanism. We know exactly how blue light disrupts melatonin, which disrupts sleep, which dysregulates the amygdala, which destabilizes emotions. Now, let me show you what happens when you get this right. In 2016, researchers at Stanford University worked with the U.S. Olympic basketball team. Elite athletes are already highly trained, physically gifted, and motivated. But the researchers wanted to see what would happen if they optimized sleep as rigorously as they optimized training. They had players extend their sleep to 10 hours per night for several weeks. Not just 8 hours, 10 hours. The results were remarkable. Free throw accuracy improved by 9%. Three-point shooting improved by 9.2%. But more importantly for our discussion, the athletes reported significant improvements in mood, decreased anxiety, and better emotional control during high-pressure games. Post-game interviews showed them responding more calmly to difficult questions, handling losses with more composure, and maintaining emotional stability, even under intense pressure. The Stanford researchers measured their reaction times and found they improved by 0.7 seconds. But they also measured subjective ratings of emotional wellness and found a 30% improvement. The athletes weren't just performing better physically, they were emotionally transformed. Their amygdalas were properly regulated. Their cortisol rhythms were optimized. Their brains were getting the REM sleep needed to process the emotional intensity of competition. This wasn't unique to basketball. The same protocols were applied to swimmers, tennis players, and track athletes with similar results. Sherry Ma, the lead researcher, found that in nearly every sport, extending sleep improved not just physical performance, but emotional resilience, team cohesion, and the ability to handle stress. Compare this to what happens in sleep-deprived populations. In 2018, researchers analyzed data from emergency room visits over a 5-year period. Looking at patterns related to sleep, they found that incidents of road rage, domestic violence, and assault all spiked on Mondays after weekend sleep disruption and declined as the week progressed and people's sleep patterns stabilized. The correlation was so strong that researchers could predict crime rates based on sleep patterns in a community. This isn't about bad people making bad choices. This is about neurologically compromised individuals whose amygdalas are hyperactive and prefrontal cortexes are impaired. Sleep deprivation doesn't excuse violence, but it helps explain the biological state that makes emotional dysregulation more likely. Let me tell you about a less dramatic, but more personally relevant example. In 2015, psychologists at UC Berkeley conducted a study on romantic relationships. They had couples track their sleep and their interactions. On days following poor sleep, both partners reported more conflict, less satisfaction, and more negative emotional exchanges. But here's what's fascinating. When one partner slept poorly, both partners reported worse interactions. Sleep deprivation in one person affected the emotional climate for both. The researchers then brought couples into the lab and had them discuss a point of conflict in their relationship: finances, household responsibilities, parenting disagreements. Half the couples did this after normal sleep. Half did it after one partner was sleep deprived. The sleep-deprived couples showed more hostility, less empathy, and an inability to de-escalate arguments. Simple disagreements spiraled into fights because one person's emotional regulation was compromised. This has profound implications. How many relationships have been damaged not by fundamental incompatibility, but by chronic sleep deprivation? How many people are in therapy for anxiety or depression that's actually rooted in sleep disruption? How many children are being medicated for emotional dysregulation when what they really need is earlier bedtimes and dark, quiet rooms? There's a common mistake people make when trying to manage their emotions. They focus entirely on daytime strategies: meditation, exercise, therapy, breathing techniques, while completely ignoring nighttime biology. These daytime strategies are valuable, but they're working against a massive handicap if you're sleeping poorly. It's like trying to bail water out of a boat while someone keeps drilling holes in the bottom. Another mistake: using alcohol to relax in the evening. Yes, alcohol initially makes you feel relaxed. It enhances GABA, an inhibitory neurotransmitter that calms neural activity. But alcohol also fragments sleep, suppresses REM sleep, and disrupts the very stage where emotional processing happens. A 2013 study found that people who regularly consumed alcohol in the evening had 40% less effective emotional memory processing compared to those who didn't. They were experiencing events, but their brains couldn't properly file away the emotional content. The unprocessed emotions accumulated like unpaid debts. Here's what actually works. Sleep hygiene focused specifically on emotional regulation. First, recognize that the 2 to 3 hours before bed are your emotional decompression zone. This is when cortisol should be dropping and melatonin should be rising. Anything that spikes cortisol during this window, Intense exercise, work stress, arguments, disturbing news, bright lights, disrupts the system. In 2019, researchers in Germany conducted an experiment where they had one group do intense email work until bedtime, and another group stop all work-related activities 2 hours before bed. The group that stopped working earlier showed 35% less amygdala reactivity the next day, and 28% better emotional regulation scores. Simply creating a buffer between stress and sleep allowed their circadian systems to function properly. The same study found that people who dimmed their lights and avoided screens in that 2-hour window had melatonin levels 50% higher than those who didn't. Higher melatonin meant better sleep, which meant better emotional processing, which meant better emotional stability the next day. Think about the cascading benefits. You protect your evening from blue light and stress, your melatonin rises naturally, you fall asleep more easily, you spend more time in REM sleep, your amygdala processes emotions effectively, your prefrontal cortex maintains control, and you wake up emotionally resilient. Each step builds on the previous one. Now, let's address something many people experience but don't understand: why anxiety often peaks at night. You've had a reasonable day, nothing terrible happened, but the moment you lie down in the dark, your mind starts racing. Worries that seem manageable during the day suddenly feel overwhelming. What's happening here is fascinating and fixable. During the day, your prefrontal cortex is active, moderating your emotional responses, keeping perspective. But as you become drowsy, the prefrontal cortex begins to shut down before the amygdala does. There's a window, usually in that drowsy state before sleep, where your emotional brain is still running, but your rational brain is offline. This is when anxious thoughts can spiral unchecked. A 2014 study from the Netherlands found that people with evening anxiety have abnormally high cortisol levels at night. Their stress hormone hasn't dropped as it should. The solution isn't sleeping pills or anxiety medication, though those have their place. The solution is resetting the circadian rhythm, so cortisol drops naturally. And the most powerful tool for this is morning light exposure. Your circadian clock is reset every morning by bright light, specifically blue light, hitting your eyes within the first hour of waking. This signals daytime to your brain, triggering the cortisol surge when you need it and setting the timer for melatonin release 14 to 16 hours later. People who get bright light exposure in the morning, preferably natural sunlight, but even a bright lamp works, have properly timed cortisol and melatonin rhythms. Those who don't, people who wake up in dark rooms, immediately put on sunglasses or work in dim offices, have disrupted rhythms that manifest as evening anxiety and poor sleep. The elegance of the system is this: your emotional stability tomorrow begins with your light exposure today and your sleep tonight. It's a continuous cycle. Disrupt one element and everything downstream suffers. Optimize one element and everything improves. Let me bring this full circle with a personal story from one of Matthew Walker's studies. He interviewed a man who'd been suffering from severe anxiety for years. The man had tried multiple antidepressants, seen therapists, practiced meditation. Nothing provided lasting relief. Then he participated in a sleep study where researchers monitored his sleep architecture. They discovered he was getting almost no REM sleep. His brain was barely entering the stage where emotional processing occurs. They worked with him to improve his sleep. Earlier bedtime, darker room, no screens, sleep extension. Within 3 weeks, his REM sleep normalized. Within 2 months, his anxiety symptoms reduced by 70%. The antidepressants that hadn't worked before suddenly became effective. His therapist noted that he was finally able to process emotions in therapy, rather than just intellectualizing them. The issue wasn't that the treatments didn't work. It was that his brain couldn't implement them without the foundation of proper sleep. This is the power and the tragedy of sleep's role in emotional health. The power is that improving sleep can cascade into massive emotional benefits: better mood, less anxiety, more resilience, stronger relationships. The tragedy is that millions of people are suffering emotionally, trying every intervention except the one that would work. Closing their eyes in darkness for 8 hours. Your amygdala is waiting. Your emotional memories are queued up for processing. Your REM sleep is standing by to run them through the non-adrenaline wash that will remove their sting. Your circadian rhythm is ready to orchestrate the perfect timing of cortisol and melatonin. The system is there, evolved over millions of years, tested and refined, ready to make you emotionally whole. But there's more to your identity than just your emotions and memories. There's something happening during those hours of darkness that's even more mysterious, even more fundamental to what makes you you. Right now, as you're listening to these words, about 60% of your brain's energy is being spent on something that has nothing to do with listening. You're not consciously aware of it, but parts of your brain are reviewing a conversation from last week, imagining a scenario that might happen next month, and replaying a memory from childhood, all simultaneously. And when you close your eyes tonight, this hidden network doesn't shut down. It amplifies. It becomes the dominant force in your consciousness. And what it creates in those wandering moments might be more valuable than anything your focused, deliberate mind ever produces. There's a network in your brain that scientists didn't even know existed until 2001. It consumes more energy than the parts of your brain that let you see, hear, speak, or move. And the reason we missed it for so long is that it only activates when you're doing nothing. When you stop trying, when you let go, when you close your eyes and drift. This is where the most profound insights emerge, not from focused effort, but from letting your mind become a time traveler, freely moving between past, present, and future. If you've ever had a brilliant idea in the shower, or solved a problem while staring out a window, or woken up with clarity about a decision that seemed impossible the night before, this section will explain why your best thinking happens when you're not trying to think at all. Give this video a like if you want to understand why doing nothing might be the most productive thing you can do. And subscribe because we're entering territory that challenges everything we've been taught about productivity, focus, and how breakthrough ideas actually happen. Let me take you to Washington University in St. Louis, 2001. Dr. Marcus Rachel, a neurologist, was conducting brain imaging studies on people performing various cognitive tasks. The standard approach was to scan someone's brain while they did something, solve math problems, read words, look at images, and see which brain regions lit up. But Rachel noticed something odd in his data. Between tasks, when participants were just resting with their eyes closed, waiting for the next instruction, their brains weren't quiet. They were burning energy at nearly the same rate as when performing active tasks. More specifically, there was a consistent pattern of brain regions that became more active during rest than during tasks. This seemed backwards. Rachel had discovered what he would later call the default mode network, a constellation of brain regions that activate when you're not focused on the external world. It includes the medial prefrontal cortex, the posterior cingulate cortex, the inferior parietal lobule, and parts of the temporal cortex. Don't worry about memorizing those names. What matters is what they do together. The default mode network is your brain's time machine. When it's active, you're not in the present moment. You're mentally simulating the future. What will I say in that meeting? You're replaying the past. Why did I respond that way? You're imagining perspectives other than your own. What is she thinking about me? You're constructing narratives about your life, your identity, your relationships. The DMN is where you exist as a continuous self across time. Rachel published his findings in 2001, and at first the neuroscience community was skeptical. This contradicted everything they thought about the brain. The assumption was that the brain had a baseline idle state and consumed extra energy only when doing work. Rachel was showing that the so-called idle state was actually the most metabolically expensive state. Your brain at rest uses about 20% of your body's total energy. When you close your eyes and let your mind wander, you're not conserving energy. You're spending it lavishly on something we're only beginning to understand. Here's what makes this profound for understanding sleep and creativity. The default mode. Network is suppressed during focused, goal-directed tasks. When you're concentrating on solving a problem, writing an email, or following directions, the DMN quiets down. But the moment you stop focusing, when you close your eyes, take a shower, go for a walk, or drift towards sleep, the DMN surges to life. And in that activation, something magical happens. In 2009, researchers at the University of British Columbia conducted a study that would revolutionize how we think about mind wandering and creativity. They had participants perform a simple, boring task, pressing buttons in response to numbers on a screen, while their brains were scanned. Periodically, they asked participants, "Were you thinking about the task or were you mind wandering?" When participants reported mind wandering, their default mode network was highly active. But here's the key finding. People whose DMN activated most strongly during mind wandering scored highest on subsequent creativity tests. The researchers then gave participants difficult creative problems to solve. Some were told to focus intensely on the problem. Others were told to let their minds wander and think about whatever came up. The mind-wandering group found more creative solutions. By not trying to solve the problem directly, they allowed their DMN to explore connections their focused mind never would have made. This explains a phenomenon that artists, scientists, and writers have known for centuries but couldn't articulate. The best ideas come when you're not working. The shower insight. The solution that appears during a morning walk. The clarity that arrives just as you're falling asleep. These aren't accidents. They're your default mode network doing what it's designed to do. Finding patterns, making connections, exploring possibility spaces. Let me give you 3 historical examples that perfectly illustrate this principle, starting with Albert Einstein. In the early 1900s, Einstein was working as a patent clerk in Bern, Switzerland. This was before his miracle year of 1905, before he was famous. When he was just a young man struggling with the deepest questions in physics. His job at the patent office was relatively mundane, examining applications for new inventions. But Einstein did something unusual during his workday. He called them thought experiments. But what he was really doing was deliberate mind wandering. He would sit at his desk, close his eyes, and imagine himself riding on a beam of light. What would he see? How would time behave? He would imagine chasing after a light wave at the speed of light. He spent hours in these reveries, not working in the traditional sense, but letting his mind explore impossible scenarios. From these daydreaming sessions came special relativity, the theory that time and space are relative, that the speed of light is constant, that mass and energy are equivalent. The most revolutionary physics of the 20th century emerged not from focused calculation, but from imaginative mind wandering. Einstein later said, "Imagination is more important than knowledge, for knowledge is limited, whereas imagination embraces the entire world." He understood intuitively what neuroscience would later prove. The default mode network, unconstrained by focused effort, can reach conclusions that directed thinking cannot. Now, let's talk about Thomas Edison, but in a different context than before. Yes, Edison famously claimed he needed little sleep, but he also famously took multiple naps throughout the day. And he had a specific technique for capturing insights from the hypnagogic state, that twilight zone between waking and sleeping, where the default mode network is most active and your conscious control is minimal. Edison would sit in a chair holding a ball bearing in each hand, with metal pie pans on the floor beneath his hands. He would relax and drift towards sleep. The moment he actually fell asleep, his muscles would relax, the ball bearings would drop and clang against the pie pans, waking him instantly. He would then immediately write down whatever images, thoughts, or solutions had appeared in that brief moment between waking and sleeping. He credited many of his inventions to insights captured this way. What Edison was doing, without knowing the neuroscience, was deliberately accessing the state where the DMN is most active while the executive control network is offline. In this state, ideas flow without the filter of logical criticism. Impossible combinations become possible. The hypnagogic state is where surrealist painters got their bizarre imagery, where musicians heard melodies that didn't follow conventional rules, where inventors saw mechanisms that hadn't been built yet. The third example is Leonardo da Vinci, perhaps the ultimate Renaissance mind. Da Vinci's notebooks reveal his extraordinary practice of deliberately cultivating mind wandering. He would stare at stained walls, at patterns in marble, at clouds, at the play of light on water, and record what his mind saw in the random patterns. He called this inducing the imagination. Oh, he understood that by letting his visual system roam freely, without trying to see anything specific, his mind would generate creative associations. Da Vinci also advocated for what he called contemplative leisure, long periods of doing nothing but thinking. He wrote that this was when his best ideas emerged, when solutions to engineering problems became clear, when artistic compositions revealed themselves. His patrons sometimes complained that he spent days staring at a painting without touching it. He was working, but not with his hands. His default mode network was exploring possibilities. In 2012, researchers at the University of California, Santa Barbara conducted a study that vindicated Da Vinci's approach. They gave participants a creativity task, then divided them into 4 groups during a break. One group rested quietly, one did a demanding memory task, one did an undemanding simple task, and one had no break at all. When they returned to the creativity task, the group that did the undemanding task, which allowed mind wandering, showed 40% improvement. The group that rested or did demanding tasks showed no improvement. The key insight is that complete rest and intense focus are both bad for creativity. What works is engaging in something easy enough that your conscious mind is occupied, but your default mode network can activate. Walking is perfect. Showering is perfect. Simple, repetitive tasks, like washing dishes or folding laundry. These activities occupy your motor system and basic attention, freeing your DMN to roam. This brings us to a critical distinction between meditation and the kind of mind wandering we're discussing. In modern Western culture, meditation is often presented as the ultimate goal, a quiet mind, present in the moment, not thinking about past or future. And meditation absolutely has benefits. Research shows it reduces stress, improves focus, and enhances emotional regulation. But meditation and mind wandering activate opposite brain networks. During focused meditation, when you're concentrating on your breath or a mantra, your executive control network is active and your default mode network is suppressed. You're deliberately preventing mind wandering. This is valuable for certain purposes, but for creativity, for making unexpected connections, for imagining novel solutions, you need the DMN active. You need mind wandering. In 2011, researchers at Yale University scanned the brains of experienced meditators during different types of practice. During focused attention meditation, the DMN was quiet. During open monitoring meditation, where you observe thoughts without directing them, the DMN showed rhythmic activation and deactivation. The meditators who reported the most creative insights were those who practiced open monitoring, allowing thoughts to arise and pass without forcing attention elsewhere. This reveals something important. The goal isn't to eliminate mind wandering. The goal is to understand when to focus and when to wander. Modern culture overwhelmingly emphasizes focus, productivity, attention, concentration. We treat mind wandering as a problem to be fixed, a sign of weak discipline. But neuroscience shows that people who can't activate their DMN have difficulty with creativity, empathy, autobiographical memory, and planning for the future. Let me tell you about a tragic case that illustrates what happens when the default mode network is damaged. In 2003, neurologists documented a patient with bilateral damage to his posterior cingulate cortex, a key hub of the DMN. The patient could function in daily life, could have conversations, could solve simple problems, but he couldn't imagine the future. When asked, "What will you do tomorrow?" he couldn't generate any scenarios. He was trapped in an eternal present, unable to mentally time travel. This revealed that the DMN isn't just for daydreaming. It's essential for constructing your sense of self across time. Without it, you can't plan, can't imagine alternatives, can't learn from past mistakes, can't anticipate consequences. The ability to close your eyes and project yourself into possible futures is what makes humans capable of complex behavior. Now, here's where sleep becomes crucial. During waking hours, even when you're mind-wandering, there's still some executive control. Your conscious mind can intervene, can judge ideas as unrealistic, can dismiss connections as irrelevant. But during that transition into sleep, the hypnagogic state that Edison deliberately accessed, executive control fades while the DMN remains active. This creates a unique window where your mind can explore without censorship. Researchers in 2017 used EEG to monitor brain waves during the transition from waking to sleep. They found that alpha waves, associated with relaxed waking, gradually gave way to theta waves, associated with light sleep and deep meditation. But during the hypnagogic state, both types of waves were present simultaneously, along with brief bursts of gamma waves, which are associated with high-level information, processing, and sudden insights. This mixed brain state is why hypnagogia is so creatively productive. Your visual cortex is generating images. Your auditory cortex is generating sounds. Your language centers are generating words. But your reality testing systems are offline. Salvador Dali, the surrealist painter, used the same technique as Edison. He would doze with a key in his hand over a plate, and the clang would wake him to capture the bizarre images emerging from hypnagogia. His paintings, melting clocks, impossible architectures, dream landscapes, came directly from this state. But you don't need to be a genius to access this. Everyone enters the hypnagogic state twice daily, falling asleep at night and waking in the morning. The question is whether you're paying attention and whether you're creating conditions for creative insights to emerge. Most people transition quickly through hypnagogia, their minds cluttered with the day's anxieties or tomorrow's obligations. But if you create mental space, finishing work hours before bed, avoiding screens, allowing time for gentle unwinding, hypnagogia becomes a portal to insight. There's a common mistake people make here, and it's the same mistake our culture makes about sleep generally, treating it as wasted time. People rush through their evening routines, collapse into bed exhausted, and want to fall asleep immediately. They see the twilight zone of hypnagogia as an inefficiency, something to minimize. But this transitional state, when your default mode network is most active and your critical faculties are quietest, is often the most creative moment of your day. Another mistake is using sleep aids, either pharmaceutical or alcohol, that knock you unconscious quickly. These substances eliminate hypnagogia. You go from awake to unconscious without passing through the creative in-between state. You're sacrificing one of the most potentially valuable moments of mental exploration. Here's what works. Create a wind-down routine that gradually reduces external stimulation while allowing internal stimulation to emerge. Dim the lights progressively. Put away devices. Engage in gentle activities that don't require focused attention. Light reading, easy stretching, listening to calm music. As you lie in bed with your eyes closed, don't try to force sleep. Let your mind wander. Notice what thoughts arise. Many people find this is when solutions to problems suddenly appear, when decisions become clear, when creative ideas emerge. In 2016, researchers in France conducted a study specifically on creative problem solving in the hypnagogic state. They gave participants a difficult logic puzzle to work on. Then they had them lie down and relax, monitoring their brainwaves. Whenever someone entered hypnagogia, detected by specific EEG patterns, the researchers gently woke them and asked what they were thinking about. In 55% of cases, people reported thinking about the puzzle, but in new ways, with different metaphors or approaches. When allowed to return to the puzzle fully awake, those who had thought about it during hypnagogia were twice as likely to solve it. This is the brain's natural creative process. Engage with a problem during waking hours. Let it go. Allow the default mode network to explore during mind-wandering or hypnagogia, and receive insights that focused effort couldn't produce. The key is trust. Trust that your brain continues working on problems even when you're not consciously thinking about them. Trust that closing your eyes and wandering isn't laziness. It's a different kind of productivity. Let me connect this to the bigger picture we've been building. Your brain during sleep isn't just maintaining itself, cleaning toxins, consolidating memories, processing emotions. It's also engaging in a kind of free exploration that's impossible during waking hours. The default mode network, freed from the constraints of reality testing and goal-directed behavior, can explore idea spaces that your focused mind would dismiss as irrelevant or impossible. This is why the most creative individuals in history, artists, scientists, inventors, writers, all emphasize the importance of rest, contemplation, and letting the mind wander. They understood intuitively that forcing creativity through sheer effort produces mediocre results. The truly novel ideas, the genuine breakthroughs, come from allowing the mind to travel freely through time, connecting past experiences with future possibilities, finding patterns that conscious analysis misses. Your default mode network is running right now. Even as you focus on these words, it's maintaining your sense of who you are, updating your mental models of other people, planning potential futures. And tonight, when you close your eyes and drift towards sleep, it will become even more active, exploring without boundaries, making connections without judgment. The question is, are you giving it the time and space to do its work? Are you rushing through hypnagogia, or are you allowing yourself to linger in that creative twilight? Because there's something even more mysterious waiting in the deeper stages of sleep, something that challenges our very understanding of consciousness itself. Last night, you experienced something that should be impossible. You were simultaneously conscious and unconscious, aware and unaware, experiencing a reality that didn't exist while your body lay completely paralyzed. You navigated worlds that defied physics, spoke with people who aren't alive, and accepted impossibilities as normal. And when you woke up, you probably dismissed it as just a dream. But what if those dreams are actually glimpses into the deepest mystery of existence, the nature of consciousness itself? Here's a question that should keep you awake at night. If you're unconscious during sleep, how can you experience dreams? If you're conscious during dreams, why can't you control them? And in that strange moment when you wake up unable to move, frozen between worlds, who or what is the you that's aware of being trapped? These aren't just philosophical puzzles. They're windows into a phenomenon so profound that we're only beginning to understand it. And the answer might redefine what we think consciousness actually is. If you've ever had a dream where you suddenly realized you were dreaming, or woken up paralyzed and terrified, or felt yourself floating between sleep and waking in a state that felt almost supernatural, this section will take you deep into those experiences. Hit that like button if you're ready to explore the strangest territories of your sleeping mind. And subscribe because we're entering realms that blur the line between science, philosophy, and the unexplained. And I promise you, understanding these states will change how you think about the nature of reality itself. Let me start with a story that sounds like science fiction, but is documented scientific fact. In 1975, a British parapsychologist named Keith Hearn was working at Hull University, trying to answer a question that seemed unanswerable. Can someone communicate from inside a dream? The problem was obvious. During REM sleep, when vivid dreams occur, the body is paralyzed. You can't speak, can't move, can't signal to the outside world. Or so everyone thought. Hearn was working with a volunteer named Alan Worsley, who claimed he could sometimes realize he was dreaming while the dream was still happening, a phenomenon people had reported for centuries but never proven. Hearn hooked Worsley up to an EEG machine and eye-tracking equipment. The plan was simple. If Worsley became aware he was dreaming, he would move his eyes in a prearranged pattern, left, right, 8 times in succession. On the night of April 12, 1975, at 8:04 a.m., it happened. Worsley was in REM sleep, his body completely paralyzed, his brain showing the characteristic patterns of dreaming. And then, suddenly his eyes moved. Left, right, 8 times. The signal. He was conscious inside the dream and communicating with the waking world. Hearn had just documented the first scientific proof of lucid dreaming, being aware that you're dreaming while the dream is still occurring. This discovery was revolutionary, but it was Stephen LaBerge at Stanford University who would turn lucid dreaming into a legitimate field of scientific research. In the 1980s, LaBerge refined the techniques, trained more subjects, and began mapping what the brain looks like during lucid dreams. What he found challenged everything neuroscience thought it knew about consciousness. During normal dreams, your prefrontal cortex, the part of your brain responsible for self-awareness, logic, and reality testing, is relatively quiet. This is why dreams are bizarre and illogical. You accept impossibilities as normal. You don't question why you can fly or why your childhood home has rooms that don't exist. But during lucid dreams, brain scans showed something remarkable. The prefrontal cortex reactivates while you're still in REM sleep. You're simultaneously in the dream state and the waking state. You have the vivid, immersive experience of dreaming, combined with the self-awareness and critical thinking of waking consciousness. LaBerge trained people to become lucid dreamers using specific techniques. The most effective was reality testing. Throughout the day, asking yourself, am I dreaming? And performing simple tests like trying to push your finger through your palm or reading text twice to see if it changes. By making this a habit during waking hours, people would eventually perform the same test in a dream, realize the text was changing, or their finger was going through their palm, and suddenly become aware they were dreaming. In a 2009 study, LaBerge had lucid dreamers perform different tasks while inside their dreams, singing, counting, or doing math problems. By monitoring their brain activity, he could see that the same brain regions activated during these dream activities as would activate if they were doing them while awake. When a lucid dreamer sang in their dream, their auditory cortex lit up. When they counted, their parietal lobe activated. The brain couldn't distinguish between the dream activity and the real activity. This raises a profound question. If your brain is generating the exact same neural patterns, whether you're singing in a dream or singing in reality, what's the difference? Which one is more real to your consciousness? Some philosophers argue this proves that consciousness is not about external reality, but about internal neural states. Your experience of reality, whether waking or dreaming, is always a construction of your brain. The only difference is whether that construction is constrained by sensory input from the external world. But lucid dreaming gets even stranger. Experienced lucid dreamers report being able to control their dreams, flying, visiting impossible places, having conversations with dream characters who seem to have independent personalities. In 2012, researchers at the Max Planck Institute in Germany studied the brain activity of frequent lucid dreamers. They found these people had larger prefrontal cortexes than non-lucid dreamers, specifically in areas associated with self-reflection and metacognition. Thinking about thinking. This suggests that the ability to be conscious of being conscious might be like a muscle that can be strengthened. And lucid dreaming might be a form of practice for enhanced self-awareness, even during waking hours. Tibetan Buddhist monks have practiced lucid dreaming for over 1,000 years as part of dream yoga, believing it helps them maintain awareness through all states of consciousness, including death. Modern neuroscience is now validating what these ancient practitioners knew. Consciousness exists on a spectrum, and the boundaries between waking, dreaming, and other states are more permeable than we thought. Now, let me take you to the darker side of this spectrum, a phenomenon that's terrified humans throughout history and has been interpreted as everything from demonic possession to alien abduction: sleep paralysis. If you've experienced it, you know exactly what I'm talking about. If you haven't, imagine this. You wake up, you're aware of your surroundings, but you cannot move. Not a finger, not a toe. You try to scream, but no sound comes out. And then, most terrifying of all, you sense a presence in the room, a shadow figure, something malevolent. It's pressing on your chest, making it hard to breathe. This happens to about 8% of people at least once in their lives, and for some, it's a recurring nightmare. Sleep paralysis occurs when you become conscious while your body is still in REM matonia, the paralysis that prevents you from acting out your dreams. Normally, consciousness and motor control turn back on simultaneously when you wake, but sometimes the timing gets out of sync. Your conscious mind wakes up, but your body is still locked in the REM paralysis state. Here's what makes it truly terrifying. During REM sleep, your brain is primed to generate vivid perceptual experiences. So, when you wake up paralyzed, your brain, still in a partially dreaming state, generates hallucinations to explain what you're experiencing. The feeling of pressure on your chest is real. It's your breathing muscles still partially paralyzed. But your brain interprets this as something sitting on you. The inability to move triggers a primal fear response. And your amygdala, your fear center, generates threatening images. Different cultures have developed remarkably similar explanations for sleep paralysis. In Newfoundland, it's called the Old Hag, a witch who sits on your chest. In Japan, it's kanashibari, being bound by invisible metal. In the Middle East, it's a jinn, a supernatural being pressing down on you. Mexican culture calls it subirse el muerto, a dead person climbing onto you. Brazilian folklore speaks of pisadeira, a crone with long nails who tramples the chests of people who sleep with full stomachs. What's remarkable is that despite having no contact with each other, cultures across the world describe the same experience: paralysis, chest pressure, and a malevolent presence. This isn't because demons or aliens actually visit people during sleep. It's because all human brains are wired the same way. When the brain finds itself conscious but paralyzed, it generates similar interpretations based on the fear response. In 2011, researchers at the University of Waterloo in Canada conducted a study on the cultural narrative surrounding sleep paralysis. They found that people from cultures with strong supernatural beliefs were more likely to interpret the experience as demonic or spiritual. People from cultures with strong science fiction traditions were more likely to interpret it as alien abduction. The hallucination adapts to your cultural framework, but the underlying experience, paralysis plus fear-generated hallucinations, is universal. But here's what's fascinating from a consciousness perspective. During sleep paralysis, you are experiencing two conflicting states simultaneously. Your body is in REM sleep paralysis. Your visual and sensory cortex are generating dreamlike hallucinations. But your prefrontal cortex is active enough to know you're in your bedroom, to recognize this is wrong, to try to move. You're neither fully asleep nor fully awake. You're in a liminal state that reveals something profound about consciousness. It's not binary. You're not simply on or off, conscious or unconscious. Consciousness exists in layers, in degrees, in states that can be partially active simultaneously. This brings us to one of the most haunting questions in neuroscience. What happens to consciousness in a coma? In 2006, a team of neurologists at the University of Cambridge made international headlines with a study that challenged everything we thought we knew about the boundary between consciousness and unconsciousness. They studied a 23-year-old woman who had been in a vegetative state for 5 months following a severe traffic accident. She showed no external signs of consciousness, no movement, no response to commands, no communication. But the researchers tried something novel. They put her in an fMRI scanner and asked her to imagine playing tennis. In healthy, conscious people, imagining tennis activates the premotor cortex, the part of the brain that plans movements. To everyone's shock, the woman's premotor cortex activated. Then they asked her to imagine walking through her house, which activates the parahippocampal gyrus involved in spatial navigation. Again, her brain activated in exactly the same pattern as a conscious person. She couldn't move, couldn't speak, couldn't signal in any way that she was aware, but her brain showed clear evidence of conscious thought, of understanding language, of following instructions. She was conscious but completely locked inside her paralyzed body. This condition is called cognitive motor dissociation, and it's now estimated that 15 to 20% of patients diagnosed as vegetative might actually be conscious but unable to respond. Think about the horror and the mystery here. Consciousness without any ability to interact with the world. Awareness without expression. These patients hear conversations, experience the passage of time, feel emotions, but exist in total isolation. From the outside, they appear identical to someone who is truly unconscious. But inside, there's a mind that's aware, that's experiencing, that's perhaps even screaming to be recognized. This raises an unsettling question. When you're in deep sleep, when your body is completely paralyzed, when you're not dreaming, when there's no conscious experience you can remember, are you actually unconscious? Or are you conscious but simply not forming memories of it? How would we know? If consciousness occurred during deep sleep, but you had no memory of it when you woke up, would it have happened? Some philosophers argue this is not just a theoretical question. They point to people who report continuous awareness through entire meditation sessions, or mystics who claim to maintain awareness even during sleep. In yoga philosophy, there's a concept called yoga nidra, or yogic sleep, a state where the body is completely relaxed as if asleep, but awareness remains. Advanced practitioners claim they can observe themselves sleeping, maintaining a thread of consciousness through states that would normally be unconscious. In 2013, researchers at the University of Wisconsin studied Tibetan Buddhist monks who had spent years practicing meditation, including techniques designed to maintain awareness during sleep. They monitored the monks' brainwaves throughout the night. What they found was extraordinary. Even during deep sleep, when delta waves normally dominate, the monks showed persistent gamma wave activity, the fastest brainwaves associated with high-level information, processing, and conscious awareness. Normal sleepers show gamma waves only during REM dreaming. These monks were showing gamma activity throughout the night, even in the deepest stages of sleep. Were they somehow remaining conscious through sleep? The monks themselves reported that they were aware of sleeping, aware of the body resting, but that some part of their mind remained alert and watchful. It's as if consciousness and sleep are not mutually exclusive, that with training, you can experience both simultaneously. This challenges our fundamental assumptions about what consciousness is. We tend to think consciousness is like a light switch, on or off, awake or asleep. But these studies suggest it's more like a dimmer switch, with infinite gradations between fully awake and completely unconscious. And different parts of your brain can be at different levels simultaneously. There's a phenomenon called local sleep that illustrates this beautifully. Researchers discovered that when you're sleep deprived, parts of your brain can fall asleep while you're still awake. In 2011, scientists in Italy monitored the brains of people who had been awake for 24 hours. They found that small regions of the cortex would start showing slow wave activity, the brain waves characteristic of deep sleep, even though the person was walking around, talking, and technically awake. This explained why sleep-deprived people make such poor decisions and have delayed reactions. Parts of their brain are literally asleep while they think they're fully conscious. You can be driving a car while portions of your visual cortex are in sleep mode. You can be having a conversation while parts of your language centers are offline. Consciousness is not a unified thing. It's a patchwork of systems that can be active or inactive independently. Now, let's tackle the deepest philosophical question. When you're dreaming, are you really experiencing anything? Some philosophers argue that dreams are retroactive constructions, that the narrative of the dream is created in the moment of waking, and the experience itself never actually occurred. It feels like you had a dream that lasted all night, but maybe your brain just generated that memory in the split second of waking. This seems absurd until you consider the evidence. Time perception in dreams is notoriously distorted. A dream can feel like it lasted for hours, but REM periods at the beginning of the night are only 10 minutes long. Did you really experience hours of dream time, or did your brain just create the memory of hours? There's no way to know for certain because the only evidence we have is memory, and memory is notoriously unreliable. In the 1960s, philosopher Norman Malcolm argued that dreaming isn't really a form of consciousness because it lacks the criteria we use to verify consciousness in others: behavior, communication, response to stimuli. A dreaming person is functionally identical to an unconscious person from an external perspective. Malcolm claimed that dreams are stories we tell ourselves about our sleep, not actual experiences that occurred during sleep. But LaBerge's lucid dreaming research demolished this argument. When lucid dreamers signal from inside their dreams using eye movements, they're proving that conscious experience is occurring in real time during REM sleep. The dream is not a retroactive construction. It's an actual experience happening while the brain is in the dream state. Consciousness during sleep is real, even if it's a strange, constrained form of consciousness, unlike waking awareness. This leads us to perhaps the most unsettling implication of all this research. You cannot actually prove you're awake right now. Your entire life could be a dream you're having in some deeper level of reality, and you'd have no way to verify otherwise. Every test you could perform to confirm you're awake, checking if text changes when you read it twice, trying to push your finger through your palm, could itself be part of the dream. The philosopher René Descartes wrestled with this question in the 1600s, concluding that the only thing he could be certain of was that he existed as a thinking entity. I think, therefore I am. But even that certainty crumbles when we consider the nature of consciousness during sleep. If you can think, reason, and have experiences in a dream that feel completely real, then thinking and experiencing don't prove you're awake. The only definitive sign that you're awake is, well, there isn't one. We navigate through life making a pragmatic assumption that we're awake because it's the most useful assumption, but it remains an assumption, not a proven fact. Modern philosophers call this the problem of phenomenal consciousness, the question of why there's something it's like to be you, why your brain's information processing is accompanied by subjective experience. We can map every neuron, measure every neurotransmitter, track every brainwave, but none of that explains why you experience the redness of red, why you feel pain, why there's an inner movie playing in your consciousness. This is called the hard problem of consciousness. And despite centuries of philosophy and decades of neuroscience, we're no closer to solving it. What sleep reveals, especially through phenomena like lucid dreaming and sleep paralysis, is that consciousness is far stranger and more flexible than our everyday experience suggests. You can be conscious without a body, as in dreams, You can be conscious while paralyzed, as in sleep paralysis. You can have different levels of consciousness in different brain regions simultaneously, as in local sleep. You can be conscious but unable to form memories, as possibly occurs in deep sleep. You can maintain awareness through states that are normally unconscious, as advanced meditators demonstrate. Each night when you close your eyes, you're not just resting your body or consolidating memories or processing emotions. You're embarking on a journey through radically different states of consciousness, exploring territories of experience that challenge our understanding of what it means to be aware, to exist, to be human. The you that goes to sleep is not quite the same as the you that wakes up, not just because memories have been consolidated or emotions processed, but because you've spent hours in states of consciousness so different from waking that they might as well be different dimensions of existence. And yet, for all this mystery, for all the strange territories consciousness travels through during sleep, your body is doing something remarkably concrete and measurable, something that determines whether you'll live to old age or die young, something so fundamental that every system in your body depends on it happening correctly every single night. If I told you there was a drug that could cut your risk of heart attack by 45%, reduce your cancer risk by 40%, prevent type 2 diabetes, strengthen your immune system better than any vaccine, and add years to your life, you'd probably ask where to buy it. Now, what if I told you that drug is free, has no side effects when used correctly, and you're already equipped to use it every single night? The drug is sleep. And the reason we don't treat it like medicine is the same reason fish don't appreciate water. It's been there all along, so we take it completely for granted. Here's a statistic that should terrify you. People who consistently sleep less than 6 hours per night have a 200% increased risk of having a fatal heart attack or stroke compared to those who sleep 7 to 8 hours. 200%. That's not a typo. Your sleep, or lack of it, is a more powerful predictor of cardiovascular disease than whether you smoke, whether you're obese, or whether you have high cholesterol. And yet, while we've launched massive public health campaigns against smoking and obesity, we've largely ignored the sleep crisis that's killing just as many people. If you've ever wondered why you seem to get sick more often when you're stressed and not sleeping well, or why your body seems to heal faster after a good night's rest, this section will reveal the molecular machinery that makes sleep the most powerful medicine in your biological arsenal. Hit that like button if you're ready to understand why sleep isn't just about feeling rested, it's about staying alive. And subscribe, because what we're about to explore will make you reconsider every night you've ever sacrificed sleep for work, entertainment, or anything else you thought was more important. Let me take you inside one of the most elegant experiments ever conducted on sleep and immunity. In 2019, researchers at the University of Tübingen in Germany recruited healthy volunteers and showed them exactly how sleep transforms the immune system at the cellular level. They took blood samples from participants after a full night of sleep and after a night of sleep deprivation. Then they isolated T cells, a type of white blood cell that's absolutely critical for fighting infections and cancer. Here's what T cells do. When they encounter a cell that's infected with a virus or has become cancerous, they need to attach to that cell and destroy it. The attachment process requires specific proteins called integrins to activate on the T cell surface. Think of integrins as hooks that T cells throw out to grab onto their targets. Without these hooks working properly, T cells can recognize the enemy, but can't actually kill it. They're like soldiers with guns, but no bullets. The researchers exposed the T cells to cancer cells in a petri dish and measured how effectively they could attach and kill. The results were stark. T cells from well-rested participants showed strong integrin activation and killed cancer cells efficiently. T cells from sleep-deprived participants, after just one night without sleep, showed 70% reduced integrin activation. They could see the cancer cells, but couldn't effectively destroy them. One night. 70% reduction in one of your body's primary cancer-fighting mechanisms. The reason for this is fascinating and reveals something fundamental about how sleep regulates immunity. During sleep, particularly deep sleep, your body releases growth hormone and suppresses stress hormones like cortisol and adrenaline. These stress hormones are important during the day. They prepare you for action, for fighting, or fleeing. But they also suppress immune function. Evolution designed it this way. If you're running from a predator, your body diverts resources away from long-term health maintenance and toward immediate survival. The problem is that chronic stress and chronic sleep deprivation acts as chronic stress, means these stress hormones never fully drop. Your immune system is perpetually suppressed. This is why stressed, sleep-deprived people get sick more often. It's not bad luck, it's biology. Your T cells are wandering around unable to properly attach to threats because stress hormones are chemically preventing integrin activation. Now, let's talk about a type of immune cell you probably haven't heard of but should know about: natural killer cells, or NK cells. These are your body's assassins. They patrol your bloodstream and tissues looking for cells that have become cancerous or infected with viruses. Unlike T cells, which need to be trained to recognize specific threats, NK cells can identify and kill abnormal cells on sight. They're your first line of defense against cancer. In 1996, researchers at UC San Diego conducted a study that should have made international headlines, but was largely ignored. They monitored NK cell activity in people who slept normally versus people who were restricted to 4 hours of sleep for a single night. After one night of poor sleep, NK cell activity dropped by 70%. Let me repeat that. One night of sleeping only 4 hours reduced your body's cancer-fighting capability by 70%. Now, extrapolate that across months or years of chronic sleep deprivation. You're giving cancer cells, which develop in your body constantly, a dramatically better chance of escaping detection and growing into tumors. This isn't theoretical. A 2003 study published in Cancer Research followed 1,240 women for 10 years. Women who consistently slept less than 6 hours per night had a 50% higher rate of developing breast cancer compared to those who slept 7 hours or more. A 2012 Japanese study following 24,000 women for 7 years found similar results. Short sleep duration was associated with significantly higher breast cancer risk. The mechanism is clear. During sleep, especially deep sleep, NK cells and T cells are manufactured, activated, and distributed throughout your body. Your bone marrow, where immune cells are produced, is most active during sleep. Your thymus gland, where T cells mature, releases more cells during nighttime hours. Your entire immune army is being recruited, trained, and deployed while you sleep. Cut the sleep short, and you're literally reducing the size and effectiveness of your immune forces. Let me tell you about a study that perfectly illustrates the real-world impact of this. In 2002, researchers at Carnegie Mellon University conducted what's called a viral challenge study. They recruited 153 healthy volunteers, monitored their sleep for 2 weeks using daily logs, and then, this is the brilliant but slightly cruel part, they gave all participants nasal drops containing rhinovirus, the common cold virus. They quarantined everyone and waited to see who got sick. The results were dose-dependent and dramatic. People who averaged less than 7 hours of sleep were 3 times more likely to develop a cold compared to those who slept 8 hours or more. But it gets more specific. Those who slept less than 5 hours were 4.5 times more likely to get sick. Same viral exposure, same quarantine conditions. The only variable was sleep. Your sleep duration literally predicted whether you'd get sick when exposed to a virus. Think about the implications during a pandemic. In 2021, during the COVID-19 crisis, researchers at multiple institutions studied the relationship between sleep and COVID outcomes. A study in France found that healthcare workers who slept less than 6 hours per night were 3 times more likely to contract COVID-19 despite using the same protective equipment as their well-rested colleagues. A study in China found that COVID-19 patients who reported poor sleep quality before infection had significantly worse disease progression and longer recovery times. But perhaps most importantly, sleep affects vaccine effectiveness. In 2020, researchers analyzed data from multiple flu vaccine studies. They found that people who slept less than 6 hours per night in the 2 weeks following flu vaccination produced less than 50% of the antibodies compared to those who slept 7 to 8 hours. Your vaccine is only as good as your immune system's ability to respond to it. If you're not sleeping, you're literally cutting your vaccine protection in half. Now, let's shift from immunity to another critical healing function: tissue repair and growth. During deep sleep, your pituitary gland, a pea-sized structure at the base of your brain, releases pulses of growth hormone. In children and adolescents, this hormone stimulates bone growth and muscle development. In adults, it's responsible for maintaining and repairing tissues throughout your body. Here's the distribution. About 70% of your daily growth hormone secretion happens during deep sleep, specifically during the first sleep cycle of the night. This is why the first 3 to 4 hours of sleep are so critical. If you go to bed at midnight and wake at 4 a.m., you might feel like you got some sleep, but you've missed the peak window for growth hormone release. Growth hormone does remarkable things. It stimulates protein synthesis, the building of new proteins that repair damaged tissues. It promotes the breakdown of fat for energy, sparing protein for repair rather than fuel. It strengthens bones by promoting calcium retention. It accelerates wound healing by promoting collagen production. It maintains muscle mass and prevents the age-related muscle loss called sarcopenia. All of this happens predominantly during sleep. In 1992, researchers at the University of Chicago measured growth hormone levels in young men under different sleep conditions. When sleep was restricted, growth hormone secretion dropped by 30% even in a single night. But more dramatically, when deep sleep was specifically suppressed, waking people briefly whenever they entered slow-wave sleep, growth hormone dropped by 80%. Even though total sleep time was preserved. It's not just about hours in bed. It's about reaching those deep sleep stages where healing occurs. Athletes have known this intuitively for decades, but the science has become increasingly precise. In 2018, researchers followed professional soccer players through a competitive season, monitoring their sleep and injury rates. Players who averaged less than 7 hours of sleep were 1.7 times more likely to suffer an injury compared to those who slept 8 or 9 hours. The mechanism is clear. Insufficient sleep means insufficient growth hormone, which means tissues don't fully repair from the micro damage that occurs during training and competition. But it's not just elite athletes. A 2014 study from Kaiser Permanente followed 1,000 patients recovering from hip fracture surgery. Those who slept less than 6 hours per night took an average of 58 days to regain mobility. Those who slept 7 to 8 hours took only 42 days, a 16-day difference in recovery time determined primarily by sleep. Your broken bone, your torn muscle, your surgical wound, all heal at a pace dictated by how much deep sleep you're getting. Now, let's talk about cardiovascular health, because this is where the statistics become genuinely frightening. Your heart and blood vessels undergo critical maintenance during sleep. Blood pressure naturally drops by 10 to 20% during sleep. This is called nocturnal dipping, and it's essential for cardiovascular health. It gives your heart and blood vessels a break from the constant pressure they endure during waking hours. People who don't experience nocturnal dipping, either because they're not sleeping or because their sleep quality is poor, are called non-dippers. And they have dramatically higher rates of heart attack, stroke, and heart failure. A 2008 study in Hypertension Journal followed 556 people for an average of 10 years. Non-dippers had more than double the risk of cardiovascular mortality compared to normal dippers. But the relationship goes even deeper. During sleep, your body performs what's essentially maintenance on your blood vessels. Endothelial cells, the cells lining your blood vessels, repair themselves, reducing inflammation and preventing atherosclerosis, the buildup of plaques that cause heart attacks. This repair process requires adequate sleep. Without it, inflammation persists, plaques build up, and cardiovascular disease progresses. In 2011, researchers at the University of Chicago did something remarkable. They recruited 495 middle-aged adults with no history of heart disease and measured their sleep duration. Then they used CT scans to look for calcium deposits in their coronary arteries, an early sign of atherosclerosis. 5 years later, they scanned them again. People who had slept less than 5 hours per night showed 83% more calcium accumulation compared to those who slept 7-8 hours. Their arteries were literally aging faster because of insufficient sleep. A massive meta-analysis published in the European Heart Journal in 2011 combined data from 15 studies involving over 470,000 people, followed for up to 25 years. The findings were unequivocal. Sleeping less than 6 hours per night increased the risk of developing or dying from coronary heart disease by 48%. And increased stroke risk by 15%. Sleeping more than 9 hours also increased risk, creating a U-shaped curve with 7 to 8 hours being the optimal range. Now, metabolic health. Your body's ability to regulate blood sugar is profoundly affected by sleep. When you don't sleep enough, your cells become resistant to insulin, the hormone that allows glucose to enter cells. In 2015, researchers at the University of Chicago took young, healthy men and restricted their sleep to 4.5 hours per night for 4 nights. By the 4th day, their insulin sensitivity had dropped by 30%, putting them in a pre-diabetic state. 4 days. The mechanism involves multiple systems. Sleep deprivation increases cortisol, which raises blood sugar. It increases ghrelin, the hunger hormone, and decreases leptin, the satiety hormone, leading to overeating. It impairs glucose metabolism directly in muscles and fat tissue. A 2013 study found that even a single night of sleep deprivation caused insulin resistance comparable to 6 months of a high-fat diet. The long-term consequences are severe. A 2005 study in the Annals of Internal Medicine followed 1,486 adults for 15 years. Those who consistently slept less than 6 hours were 7.5 times more likely to develop type 2 diabetes compared to those who slept 7 to 8 hours, even after controlling for body weight, physical activity, and family history. Sleep deprivation is an independent risk factor for diabetes on par with obesity and sedentary lifestyle. Let me share a case study that brings all of this together. In 2017, Dr. Michael Roizen, Chief Wellness Officer at the Cleveland Clinic, published data on a 52-year-old executive who came to him with multiple health problems: pre-diabetes, high blood pressure, high cholesterol, 40 pounds overweight, chronic fatigue, and frequent colds. The standard medical approach would be multiple medications: statins for cholesterol, metformin for blood sugar, antihypertensives for blood pressure. Instead, Roizen focused primarily on sleep. The executive was sleeping 4 or 5 hours per night, frequently using sleeping pills, and had untreated sleep apnea. They treated the sleep apnea with a CPAP machine, gradually extended his sleep to 7.5 hours per night without sleeping pills, and established a consistent sleep schedule. 6 months later, every single health metric had dramatically improved. Blood pressure normalized, cholesterol dropped, blood sugar normalized, no longer pre-diabetic. He lost 28 pounds without changing his diet. His energy returned and he stopped getting frequent colds. This wasn't miracle medicine. This was allowing the body's natural healing mechanisms, all of which operate primarily during sleep, to function properly. The medications might have addressed symptoms, but sleep addressed root causes. Now, let's talk about longevity, because this is where the data becomes most compelling. The longest running and most comprehensive studies on human longevity all point to the same conclusion. 7 to about 8 hours of sleep per night correlates with the longest lifespan. Less than that, you die younger. More than that, you also die younger, though the excess sleep might be a marker of underlying health problems rather than a cause. The Nurses' Health Study, which followed over 71,000 women for 10 years, found that women who slept less than 5 hours per night had a 15% higher mortality rate compared to those who slept 7 hours. Women who slept 9 or more hours had a 30% higher mortality rate. The Million Women study in the UK, following 1.3 million women, found similar patterns. The sweet spot, the sleep duration associated with the longest life and healthiest aging, is consistently 7 to 8 hours. But it's not just duration, it's quality and consistency. A 2018 study in the Journal of the American Heart Association followed 1,654 adults over age 60 for 5 years. They measured not just sleep duration, but also sleep regularity, how consistent bedtimes and wake times were across the week. People with irregular sleep schedules had nearly twice the risk of cardiovascular events compared to those with consistent sleep, even if their average sleep duration was the same. Think about what this means for the modern world. We've created a culture that glorifies sleep deprivation. "I'll sleep when I'm dead" is a badge of honor. Corporate culture rewards those who work late and start early. Medical residents still work 24-hour shifts despite overwhelming evidence of harm. We've normalized the very behavior that's literally shortening our lives. The tragic irony is that sleep deprivation reduces productivity. A 2011 study estimated that sleep-related problems cost the U.S. economy $63.2 billion annually in lost productivity. Workers who sleep less than 6 hours are significantly less productive than those who sleep 7 to 8 hours. But they're often praised for their dedication to working long hours. We're sacrificing both health and effectiveness in service to an outdated cultural ideal. Here's the common mistake that kills. People know they should sleep more, but they view it as something they'll prioritize when things calm down. After this project, once I get promoted. They treat sleep as discretionary, something to fit in if there's time left over after everything else. But your body doesn't wait for convenient timing. The damage accumulates every single night. The cardiovascular disease develops. The immune system weakens. The metabolic dysfunction progresses. And by the time symptoms appear, the heart attack, the cancer diagnosis, the diabetes, years of damage have already occurred. Another critical mistake, believing you can catch up on sleep on weekends. Yes, sleeping in on Saturday and Sunday can help you feel less tired, but it doesn't undo the metabolic, immune, and cardiovascular damage from chronic sleep deprivation during the week. Your body needs consistent, adequate sleep every night. It's like nutrition. You can't eat only on weekends and expect to be healthy. The solution isn't complicated, but it requires a fundamental shift in priorities. Sleep needs to be treated like any other critical health behavior, something you schedule, protect, and refuse to compromise on. You wouldn't skip taking life-saving medication because you're busy. Sleep is life-saving medicine, and it deserves the same respect. Every night that you choose 7 to 8 hours of sleep, you're choosing stronger immunity, better cardiovascular health, optimal metabolic function, effective tissue repair, and longer life. You're reducing your risk of heart attack, stroke, cancer, diabetes, Alzheimer's, and premature death. You're not just feeling better, you're measurably, biologically extending your healthy lifespan. But sleep isn't just about your body's biology operating in isolation. There's something even more profound happening. A connection between your internal rhythms and the vast cosmos beyond your bedroom walls. Every night when you close your eyes, you're not just participating in a biological process. You're synchronizing with a rhythm that's been playing since the Earth first began to spin 4.5 billion years ago. Your sleep is not separate from the cosmos. It's a direct response to it. The same rotation that creates day and night, that governs ocean tides, that determines seasons, is also governing the opening and closing of your eyes. You are not just on Earth. You are Earth, experiencing its daily dance with the sun through your own consciousness. And here's what should fill you with awe. Right now, as you listen to this, there are astronauts orbiting 250 miles above us on the International Space Station, circling the Earth every 90 minutes, witnessing 16 sunrises and sunsets every single day. And their sleep, their very biology, is in chaos because they've been separated from the ancient rhythm that created them. Studying what happens to them reveals something profound about what makes us human and what we desperately need to survive. If this entire journey through the science of sleep has resonated with you, if you're seeing sleep differently now, not as wasted time, but as the foundation of everything you are, show your appreciation by hitting that like button one last time. And if you've made it this far, you're clearly someone who values deep understanding. So subscribe, because this is just the beginning of exploring the profound connections between our bodies, our minds, and the universe we inhabit. Now, let's bring this all home. Let me take you to 1962, deep in a cave in southwest France called Midnight Cave, Grotte de Minuit. A French geologist named Michel Siffre had a radical idea. What would happen to the human body if it was completely separated from all time cues? No sunlight, no clocks, no schedules. He descended into the cave on July 16, 1962, planning to stay for 2 months in complete darkness and solitude. Siffre had a telephone line to the surface. Every time he woke, ate, or went to sleep, he would call the team above. They recorded the times, but never told him what time it actually was. He had no way of knowing whether it was day or night, whether hours or days had passed. He was testing whether the human body had an internal clock independent of external cues. What happened was extraordinary. Despite having no time information whatsoever, Siffre naturally settled into a rhythm of approximately 24 to 25 hours. He would be awake for about 16 hours and asleep for about 8-9 hours. His body temperature rose and fell on a 24-hour cycle. His cortisol and melatonin cycled on a near 24-hour rhythm. Even isolated from the Earth's rotation, his body was still following it. When Siffre emerged on September 14th, he thought it was August 20th. He had completely lost track of time consciously, but his body had been keeping time unconsciously with remarkable precision. This was the first compelling evidence that humans have an internal biological clock that approximates Earth's 24-hour rotation even without environmental cues. This internal clock is called the circadian rhythm, from the Latin circa diem, meaning about a day. And it's not unique to humans. Every organism on Earth that's been studied, from single-celled bacteria to plants to insects to mammals, has circadian rhythms. This makes sense when you think about it evolutionarily. Life evolved on a planet that rotates every 24 hours, creating a reliable cycle of light and darkness. Any organism that could anticipate this cycle, that could prepare for dawn before it arrived, that could prepare for night before darkness fell, had a survival advantage. In 2017, the Nobel Prize in Physiology or Medicine was awarded to 3 American scientists, Jeffrey Hall, Michael Rosbash, and Michael Young, for discovering the molecular mechanisms of the circadian clock. They worked with fruit flies and identified the genes and proteins that create this 24-hour rhythm. What they found was beautiful in its elegance. A protein called PER accumulates during the night and degrades during the day, creating a feedback loop that oscillates with a period of approximately 24 hours. But here's what makes it cosmic. This mechanism is not localized to one part of your body. You don't just have one clock, you have trillions. Nearly every cell in your body has its own circadian clock, its own cycling of clock genes and proteins. Your liver cells have a clock that times when to metabolize nutrients. Your immune cells have a clock that times when to be most active against infections. Your brain cells have clocks that time when to be alert and when to sleep. You are not a single organism. You are a galaxy of trillions of cells, all keeping time together, all synchronized to Earth's rotation. And the conductor of this cellular orchestra? A tiny region in your brain called the suprachiasmatic nucleus, or SCN, a cluster of about 20,000 neurons sitting right above where your optic nerves cross. The SCN receives direct input from specialized cells in your retina that detect light, specifically blue light in the 460-480 nanometer wavelength. When morning sunlight hits your eyes, these cells signal the SCN, which then broadcasts to every cell in your body. It's daytime. Adjust your rhythms accordingly. This is why light is so powerful for regulating sleep. It's not just about making you feel alert. It's about synchronizing trillions of cellular clocks to the external day-night cycle. And the most effective time for this synchronization is the first light of morning. When you expose your eyes to bright light within the first hour of waking, preferably natural sunlight, but even bright artificial light works, you're telling your entire body what time it is. In 2002, researchers at Thomas Jefferson University conducted an elegant study showing just how powerful this is. They had one group of people get 30 minutes of bright light exposure within an hour of waking every day. Another group got the same amount of light exposure, but in the evening. After 2 weeks, the morning light group showed robust circadian rhythms with clear peaks of cortisol in the morning and melatonin at night. The evening light group had disrupted rhythms, trouble falling asleep, and worse mood. This brings us to modern life's most destructive invention for sleep: artificial light, specifically at night. For millions of years, humans lived in perfect synchrony with the sun. When the sun set, darkness fell, and within a few hours, sleep followed. The invention of fire extended our waking hours slightly, but firelight is predominantly in the red-orange spectrum, wavelengths that don't significantly suppress melatonin. Then came electric lighting. In 1879, Thomas Edison invented the practical incandescent light bulb, and by the early 1900s, electric lighting was spreading through cities. For the first time in human history, darkness was optional. People could stay awake long past sunset, working, reading, socializing under artificial suns. Average sleep duration began to decline, from 9 hours per night in the 1800s to 7.5 hours by the 1950s to less than 7 hours today. But the real catastrophe came with LED lights and electronic screens. LEDs emit powerful blue light, the exact wavelength that most effectively suppresses melatonin and signals to your SCN that it's daytime. In 2011, researchers at Rensselaer Polytechnic Institute measured the effects of different light sources on melatonin. They found that 2 hours of LED light exposure in the evening suppressed melatonin by 22% compared to dim, incandescent lighting. Electronic screens, phones, tablets, computers, are even worse because we hold them close to our faces, maximizing light exposure to the retina. A 2014 study published in Proceedings of the National Academy of Sciences compared people reading on iPads versus reading printed books before bed. The iPad readers took 10 minutes longer to fall asleep, had 55% less melatonin production, experienced less REM sleep, and reported feeling sleepier the next morning despite sleeping the same number of hours. The blue light from the screen was telling their bodies it was still daytime. disrupting every aspect of sleep architecture. This is why your evening screen time isn't just keeping you awake, it's desynchronizing you from the planet. Your cells are receiving conflicting information. The rotation of the Earth says it's night. Your screens say it's day. And your body, trying to navigate these mixed signals, ends up in a state of chronic jet lag. Which brings us to astronauts, and one of the most fascinating natural experiments in human circadian biology. When astronauts go to the International Space Station, they're orbiting Earth every 90 minutes, experiencing a sunrise and sunset every 45 minutes. Their circadian rhythms are completely disrupted. Early space missions reported severe sleep problems, astronauts sleeping only 5 to 6 hours per night, despite being scheduled for 8, frequent awakenings, and difficulty falling asleep. In 2016, NASA scientists published comprehensive data on astronaut sleep. They found that 75% of astronauts use sleep medication during missions, far higher than their usage on Earth. Sleep quality was poor, and cognitive performance suffered. This wasn't just about the stress of spaceflight. It was about fundamental desynchronization from Earth's 24-hour cycle. NASA's solution was elegant. They installed special LED lighting systems on the ISS that change color temperature throughout the day. In the morning, the lights emit blue-enriched light to signal daytime to astronauts' circadian systems. In the evening, the lights shift to warm, red-enriched light that doesn't suppress melatonin. This artificial day-night cycle, even in the absence of Earth's actual rotation as a cue, improved astronaut sleep duration by 30 minutes per night and reduced sleep medication use. This has profound implications. If astronauts in space can improve sleep by manipulating light, so can you. The principle is simple. Make your environment match the natural light cycle Earth evolved under. Bright, blue-enriched light during the day, especially morning. Dim, warm light in the evening. Complete darkness at night. But there's an even deeper connection between sleep and the cosmos that I want to share with you. In 2014, astronomers discovered something remarkable about human melatonin, the same molecule that regulates your sleep. The hormone secreted by your pineal gland in response to darkness is also produced by many plants and even some bacteria. More than that, melatonin has powerful antioxidant properties. It protects cells from radiation damage. Some scientists now hypothesize that melatonin's original evolutionary function may have been protection against cosmic radiation. Earth's atmosphere shields us from most cosmic rays, but before the ozone layer developed, early life forms needed protection from harmful radiation. Melatonin may have evolved as a cellular shield. Later, as complex organisms evolved, this radiation protective molecule was repurposed as a signal for darkness and sleep. If this is true, and the evidence is compelling, then melatonin connects you to the cosmos in a direct, physical way. The molecule that tells you it's time to sleep is the same molecule that protected your ancestors from cosmic rays billions of years ago. Your sleep is not just responding to Earth's rotation. It's part of life's ancient adaptation to existence in a universe filled with radiation from distant stars. Let me bring this full circle to where we started, the question of why sleep exists at all. We've explored the cleaning, the consolidation, the emotional processing, the immune function, the healing, the consciousness. But underlying all of it is this: sleep is the way biology synchronizes with cosmology. Your body needs to be in phase with the planet. The rotation of Earth creates opportunities and threats on a 24-hour cycle. Light means warmth, visibility, time for activity. Darkness means cold, vulnerability, time to hide and repair. For 4 billion years, life has been refining its response to this cycle. Sleep is not a bug in the system that evolution hasn't fixed. It's the feature that allows complex life to exist on a rotating planet. And every adaptation we've discussed, the glymphatic cleaning, the memory consolidation, the immune boost, the growth hormone release, evolved because sleep provided a protected window when these energy-intensive processes could occur without competing with waking demands. You are not separate from nature. You are not separate from the cosmos. When you close your eyes tonight, you're participating in a ritual as old as life itself, as fundamental as the Earth's spin, as cosmic as the sun's light, reaching across 93 million miles of space to signal your cells about the rhythm of existence. So, what does this mean practically? How do you honor this cosmic connection in your daily life? Let me give you a framework, not rigid rules, but principles that align your biology with the planet's rotation. First, anchor your day with light. Within 30 to 60 minutes of waking, get outside if possible. Even 10 minutes of morning sunlight signals your circadian system powerfully. If you live somewhere with limited morning light or wake before dawn, consider a light therapy box, 10,000 lux for 20-30 minutes while you have breakfast or coffee. This one practice will cascade into better sleep 14-16 hours later. Second, create a sunset in your home. About 2 to 3 hours before your intended bedtime, begin dimming lights. If you have smart bulbs, program them to shift toward warmer colors. If not, use lamps with warm-colored bulbs instead of overhead lights. You're mimicking the natural transition from day to night that your ancestors experienced for millions of years. Third, respect the screen problem, but be realistic. Completely avoiding screens in the evening might not be feasible for your life, but you can minimize the damage. Use night mode or blue light filters on all devices. Reduce screen brightness and try to stop scrolling at least 30 from 60 minutes before bed. If you must use devices, keep them at arm's length rather than inches from your face. Light intensity decreases with distance. Fourth, make your bedroom a cave. Darkness matters. Even small amounts of light can suppress melatonin. Use blackout curtains or a sleep mask. Cover any LED lights from electronics. That little charging light or the glow from your alarm clock is enough to disrupt sleep. Temperature also matters. Cooler is better, around 65 to 68 to chest Rs, 18 and 20 degrees. Your body temperature naturally drops during sleep, and a cool room facilitates this. Fifth, establish a wind-down ritual. This doesn't need to be elaborate, just consistent. Your brain loves predictability. When you do the same things in the same order each night, your brain learns. These actions precede sleep. It could be as simple as dimming lights, gentle stretching, reading a few pages of a physical book, then bed. The specific activities matter less than the consistency. Sixth, protect your sleep like you protect anything precious. Schedule it, defend it, say no to things that would compromise it. This isn't selfish, it's self-preservation. You cannot be your best self for your family, your work, your community, if you're running on insufficient sleep. Now, I know some of you are thinking, this all sounds great, but my life is complicated. I have a newborn, I work night shifts, I have insomnia, I have sleep apnea. And you're right, sleep disorders and life circumstances are real. If you suspect you have a sleep disorder, please see a sleep specialist. Medical conditions like sleep apnea, restless leg syndrome, or chronic insomnia need professional treatment. But for the majority of people, poor sleep is not a medical disorder. It's a lifestyle disorder. It's the accumulated consequence of living in a world that's out of sync with our biology. And the beautiful thing is that your biology is patient. It's waiting. Your circadian clocks are ready to sync up. Your glymphatic system is standing by. Your immune cells are prepared to proliferate. Your memories are cued for consolidation. Your emotional wounds are ready to heal. All of it is there, this incredible machinery of repair and renewal built over 4 billion years of evolution, tested and refined, ready to serve you. The question is, will you let it? I want to leave you with one final thought, one that encompasses everything we've explored over this journey. When you close your eyes tonight, you're not just going to sleep. You're participating in something ancient and cosmic. You're allowing your brain to clean itself of proteins that cause dementia. You're consolidating memories, turning experience into wisdom. You're processing emotions, integrating yesterday's pain into today's resilience. You're boosting your immune system, preparing to fight infections and cancer. You're healing tissues, building muscle, strengthening bones. You're synchronizing trillions of cellular clocks to Earth's rotation. You're connecting with a rhythm that's been playing since the planet was born. Sleep is not wasted time. It's not laziness. It's not a luxury. It's the foundation of everything that makes you human. Your health, your happiness, your creativity, your compassion, your wisdom, your very life. And in a world that constantly tells you to do more, to achieve more, to sleep less. Choosing to close your eyes for 7-8 hours is an act of profound self-respect and wisdom. The most relaxing fact about your mind is this: when you close your eyes, you don't need to do anything. You don't need to control, to plan, to worry, to achieve. You just need to trust. Trust that your brain knows what to do. Trust that 4 billion years of evolution have prepared your body for this. Trust that the darkness is not emptiness, but fullness, full of healing, full of growth, full of transformation. So, tonight when you lay your head down, remember, you're not alone in the darkness. You're joined by every human who's ever lived, every ancestor who's ever closed their eyes and trusted in sleep's embrace. You're joined by every creature on Earth following the same rhythm. You're joined by the very spin of the planet beneath you, the sun that will rise again, the cosmos that created you and continues to hold you. Close your eyes, let go, and trust that when you open them again, you'll be renewed, restored, and ready to embrace another day of this extraordinary experience we call being alive. Thank you so much for joining me on this deep dive into the science and wonder of sleep. If this journey has changed how you think about closing your eyes, if it's given you new appreciation for those hours of darkness, I'd be honored if you'd share this with someone who needs to hear it. We're all in this together, all trying to navigate a modern world that's often at odds with our ancient biology. And please, stick around for what comes next. We have so many more mysteries to explore. The quantum nature of consciousness, the mathematics of dreams, the connection between sleep and creativity, the future of sleep technology, and so much more. The cosmos is vast, the mind is deep, and we've only just begun to understand how the two are connected. Until then, sleep well, dream deeply, and remember, every time you close your eyes, you're touching infinity.